Hello, check. Alright, people. I believe now you'll be able to hear me properly. Welcome to the session. Thank you so much for waiting. Thank you so much for your patience, as always. Welcome to the session. Finally, we are live. So, my dear friends, as you already know from the title of this session, that we are going to target inorganic chemistry. And what we will be doing is we will be revising all the concepts of inorganic chemistry. Yes, and thankfully for inorganic chemistry we have only 2 chapters. Thank God. So we've got coordination chemistry and we've got D and F block. And the good thing about it is that the questions will be very limited, very theoretical in nature, and these questions will be asked from the NCERT. Simple as that. There is no rocket science over here. So this is going to be a very simple exercise to revise these ideas. So what we'll try to do is, we'll try to trigger our minds, we'll try to trigger the concepts in our minds via questions. So you can say, we'll do revision via questions. We'll revise the full concept, don't worry about that part, but we'll trigger that concept via questions. Alright, so the first thing that we'll do today, I'll introduce myself to you as well. The first thing that we'll do today is we'll target coordination chemistry chapter, because this is a little more logical. DNF block is more memory based, so we will do that when we do that. First, we'll do coordination chemistry, and the very first thing in coordination chemistry that we will revise is the nomenclature. Yeah. So you can expect one question in your board examinations, a small question. Generally, it is a 2 mark or a 4 mark question, depends on what their mood is. So generally, it's a small question asking you about the names of these particular compounds. Right. So, my dear friends, let us remember and revise what are the rules of nomenclature. But before that, let me introduce myself to you. My name is Pahul. I'm an alumnus of IIT Bombay, and I've been teaching chemistry for around a decade now. And these are a few of my hobbies that are written over here. That's me on my Ducati Diavel, in case you are interested in motorcycles, you know. Cool. Alright, so we'll get into coordination chemistry. If there are any problems with the sound, etc., please let me know. Alright, Harita, so around 2 hours per chapter, you can say. Could be less also, because not wait, let me check if there are any problems with the audio. Hello, check. Okay, seems fine to me. Okay, audio is fine, bro. Did you check? Coolio. Valatya, I will definitely look at the chat as well. Okay, so my dear friends, how do we think about the nomenclature? Let us quickly refer to the NCERT for the rules of nomenclature. It's very easily mentioned in the NCERT. It's just a set of rules that we have to follow. Yeah. So first few rules that are written over here, the same thing we will do from the NCERT also. Any problem with the audio, bro? Multiple source selected or what? Ah, that's why. Got it. Yeah, people, now the echo will not be there. So the same audio was on from 2 different sources, and that creates an echo. Now the echo would go away. Alright, perfect. So people, this is the excerpt that I've taken from the NCERT directly. Let's read it carefully. Okay. So formula for compound is a tool used to provide basic information. We all know that. Let's read the rules. Central atom is listed first. The ligands are then listed in alphabetical order. The placement of ligand in the list does not depend on its charge. It's simply done in alphabetical order. Right? Now, polydentate ligands are also listed alphabetically. In case of abbreviated ligand, the first letter of the abbreviation is used to determine the position of the ligand in the alphabetical order. Fine. So, alphabetical order is important for us. The formula for the entire coordination entity, whether charged or not, is enclosed in square brackets. For the coordination sphere, we have to put those names in square brackets. Now, when ligands are polyatomic, their formulas are enclosed in parentheses. Do you understand what parentheses means? Parentheses means these round brackets. Okay. So, when ligands are polyatomic, their formulas are enclosed in parentheses. Ligand abbreviations are also enclosed in the parentheses. There should be no space between the ligand metal within a coordination sphere. When a formula of the charged coordination entity is to be written without the counter ion, the charge is indicated outside the square bracket, something like this. Okay. So, the question could also be, write the formula for the given name. So, you have to make sure this is how we write that particular formula. We'll come to name rules also, formula rules. They will look like this, very easy. The charge of the cation is balanced by the charge of the anions. Okay, fine, this is simple. But now, let's come to the rules of writing names via these formulae. So, I'll simply open the NCERT for you because this is exactly where we revise these ideas from. So, look at this. The cation is named first in both positively and negatively charged coordination entities. Okay. So, please remember this idea that the cation is named first. That's very important for us to remember. Then, the ligands are named in an alphabetical order before the name of the central ion. So, in the formula, first you name the ligands in alphabetical order, then you name the central metal. Okay. Names of the anionic ligands. This is very important and people generally forget this idea. Names of the anionic ligands end in O. Alright. Names of the anionic ligands end in O. And for those of neutral and cationic ligands, they are the same. So, for H2O, aqua, for NH3 amine, for CO carbonyl, for NO nitrosyl. While writing the formula of coordination entity, these are enclosed in brackets. So, this O is very important over here. If you have Cl negative ion, what will be the name of this particular ligand in nomenclature? This will be called chlorido. You won't call it the chloride ion. You would call it chlorido. Alright. If you have bromide ion, Br negative as the ligand, this will be called bromido. Yes. If I have, let's say, the oxalate ion, if this is my ligand, then what will we call this? We will call this oxalato. Alrighty. So these are the ideas behind naming the anionic parts of ligands, right? So this is done. These 3 points we understand. Let's move to the next point. Prefixes mono, di, tri, etc. are used to indicate the number of individual ligands in the coordination entity, but when the names of the ligands themselves include a numerical prefix, then the term bis, tris or tetrakis, etc. is used. For example, if in any particular coordination sphere you have 2 ethylene diamines, yeah, we can write this as ethylene diamine, right? But since the name of this species itself has a di in it, I have to mark this 2 also. So to mark that 2, I will write bis ethylene diamine. So because the name of the ligand itself has a di, I don't want to say diethylene diamine. That sounds weird for the lack of better words. Yeah. So what we will do is we will call it bis ethylene diamine. Fine. So that's how we work. If the di, tri, etc. is inside the name itself, then we use bis, tris, tetrakis. Cool. So look at this example also. NiCl2 PPH3 whole twice. How will we name this particular species? We'll call it dichlorido bis triphenyl phosphine nickel 2. Just have a look at the name. Okay, dichlorido bis triphenyl phosphine nickel 2. So why did we keep chlorido first and triphenyl phosphine later? Because when we compare the alphabets of these two ligands, I'm comparing the C of the chloro with the T of the triphenyl phosphine. So if you remember A, B, C, D, you remember A, B, C, D, right? So in A, B, C, D, C comes first. That's why we keep chlorido first and then we keep the triphenyl phosphine. Alright, so that's how this works. Now, oxidation state of the metal cation, anion or neutral coordination entity is indicated by Roman numerals in parentheses. This one. So the coordination number of nickel will be written next to it in Roman numerals with brackets. If the complex ion is a cation, the metal is named same as the element. For example, over here we have a nickel 2 positive, right? So nickel cation will simply be called nickel 2. But if the complex is an anion, the name of the metal ends with the suffix ate. For example, cobalt in a complex anion. Look at this. Tetra. What is the name of this ligand, people? Thiocyanato. SCN refers to thiocyanato. Yes. So tetra thiocyanato cobaltate. That is what we will call it, because the entire species is an anion. The entire coordination entity is an anion and therefore its name should end in ate. So tetra thiocyanato cobaltate. Fine. So that's why we will use cobaltate over here. Acha, what's the oxidation state of cobalt in this? What is the oxidation state of cobalt over here? SCN. Okay, SCN has a negative charge on it. Total, I have 2 negative charges outside. So what should be the charge on cobalt? So SCN negative into 4. This is basically 4 negative. Out of 4 negative, 2 negative is outside. So 2 positive should be there on cobalt. Fine. So tetra thiocyanato cobaltate 2 ion. If you have to write the entire name of this species, this will be called tetra thiocyanato cobaltate 2 ion. This entire species. Cobaltate. 8 means overall it is an ion. Okay. So Skew is saying, why did we write ion over here? Very good question. See, right now, do we have any cation stabilizing this charge? Since we do not have any cation stabilizing this charge, I write ion over here. Simple. If I put potassiums over here, let's say I put 2 potassiums to balance it, then I will write potassium tetrathiocyanato cobaltate. We will not write ion in that scenario. So if an ion is mentioned separately, I add the word ion at the end of the name. Alright, that's how nomenclature for coordination entities works. Alright, so let's look at this case. The neutral complex molecule is named similar to that of the complex cation, no problem over there. Let's look at this particular example. So what are the ligands that we have over here? You can read it. What are the ligands that we have over here? We have amine. In coordination compounds, NH3 is written as amine with 2 M's. H2O is aqua. And this is your chloride. But is chloride a ligand over here? Is chloride a ligand? Chloride is not a ligand. Chloride is the counter ion. So this chloride over here is not a ligand. It is just the counter ion. It is sitting outside the coordination sphere. So this is the coordination compound. The outside thing is just to satisfy the charge. right? So the name will include this, and at the end we'll say chloride. Look at the name. Triamine, triaqua, chromium 3 chloride. Notice one thing. For the counter ion, did I put the number over here? Did I write trichloride? I simply wrote chloride. You don't have to mention the number of the counter ion outside. The number of counter ion does not matter in the name. Why does it not matter? Because we are scientists, we can figure out how many chlorides we should have. So Kevin is saying, sir, why is tris not used over here? Because in the name amine, you don't have a bi-di-tri. In the name aqua, we don't have bi-di-tri. So if in the name of the ligand only, I have bi-di-tri, like triphenylphosphine, like ethylene diamine, there we will use bis tris tetrakis. But these are simple names, so you will use bi-di-tri. Okay. You will use simple names over here, di, tri, etc. Cool. So this is one example. Another example, look at this one. What is the ligand this one called? This ligand is called ethylene diamine or ethane 1,2-diamine. Both are fine, okay? If you write ethylene diamine in your board examination, that will also give you full marks. So you can write this also, ethylene diamine. This is also fine. Ethane 1,2-diamine is also fine. Both are fine. Since NCERT gives this, prefer that you read it this way, but that's also absolutely perfect. You accept it, no problems whatsoever. So now notice, since the name of this ligand itself has a di inside it, the prefix that we will put for the 3 will not be tri anymore, it will be tris. Tris, ethylene diamine, cobalt 3 sulfate. Yeah. So this is where we will use the prefix tris. Fine. That's how it's going to work. How to calculate the number which we write. Darshini, that is called the oxidation state, and we will look at further examples and then we'll see how to figure out the oxidation state. Yeah. Look at this particular case. Before I give you the answer, can you try to answer this in the chat, please? AgNH32, AgCN2. Try to answer in the chat, please. So first you name the cation part, then you name the anion part. Yeah. So AgNH32, first thing has to be the cation. That is the convention that we follow over here. The convention that we follow is that the first thing has to be the cation and the second thing has to be the anion. Okay, fine. So now, can you try to figure out the name? Sarunika, I have put that PDF in a bunch of comments from the yesterday's session. You can check out those comments. I will tell my team to share a fancy version of it as well. Physical chemistry we have scheduled for Wednesday, people, at 1 p.m. Kevin, can you give the oxidation state of silver also? What will be the oxidation state of silver? Let's think. What should be the name? This should be diamine. First is cation, so we don't need to put A to it over here. Diamine silver. What's the oxidation state of silver? Silver exists in +1 oxidation state. 1 Roman numeral. Diamine silver 1. Simply do this. Absolutely fine. And then what is this? Di-cyanato. Yes, di-cyanato. Will we write silverate? No, silverate does not sound good. We'll write argentate. For these type of metals, we will use their Latin name derivatives. For iron, we'll use ferrate. For silver, we'll use argentate. For lead, we'll use plumbate, something like that. Okay. So dicyanato argentate. And what's the oxidation state of silver? Once again, it is 1. Okay, fine. So let's check. Diamine silver 1, dicyanido argentate 1. Cool. So cyanido is the IUPAC name of C triple bond N. So please don't write cyanato, write cyanido only. This is accepted by IUPAC. Alright, cool. Bharadwaj, so in the cation part, we write the name of the metal as it is. So for the cation part, we will write only silver. For the anion part, we will write the metal's name with 8 at the end. So when we have to write 8, silverate sounds bad. Therefore, we use argentate. Okay, fine. So diamine silver 1, dicyanido argentate 1. Now, why is the oxidation state of silver +1? See, first of all, it is common knowledge that silver gives you +1 oxidation state most of the time. Remember Tollens reagent from yesterday's class, silver was +1 over there also. But at the same time, we can think about the charges. What is the charge on cyanide? Cyanide is -1. What's the charge on ammonia? The charge on ammonia is 0. So if the charge on this silver is +1 and charge on this silver is also +1, +1, +1, -1 into 2, full charge balance. There is no charge written outside, so full charge has to be balanced. That's why silver +1 makes sense over here. Alright. So Harita, when both the cation and the anion are mentioned right next to each other, then we do not need to use the word ion. Okay, fine. So in this case, we don't need to use the word ion. Why? Because cation is balanced by anion. But if we look at this particular situation, I have only anion over here. I do not have any cation over here. So since this anion is sitting alone, when we name this anion, we will write ion at the end. Okay. So now let us try to go back to this question and let's try to name these species. Okay. Shall we? First one. What are the ligands that we have? One ligand is amine. The other ligand is a chlorido. And this one is what? NO2. NO2 is called nitrito N. Okay, this NO2 is called nitrito N. If you write this like ONO, so there are two possibilities in which nitro can react with the metal. You can have MnO2 or you can have MoNO. In the first case, we call it nitrito N. In the second case, we call it nitrito O. That's the difference, because over here nitrogen is bonding to the metal, over here oxygen is getting bonded to the metal. So that's how it works, right? Fine. All right. So people, how would we name this? Amine, chlorido and nitrito. First we'll have to name amine. Alphabetically this comes first. So tetraamine just a second. So we've got tetraamine. Then we've got one single chlorido. Then we've got one single nitrito N, cobalt, because that part is the cation, no? So we don't have to write cobaltate, we simply write cobalt. What's the oxidation state of cobalt over here? Can you tell? What is the oxidation state of cobalt? So this is Cl-1, this is Cl-1, This is NO2. What will be the charge on NO2? Yeah, the charge on NO2 will also be a negative charge, right? NO2 negative. So, people, what should we call it eventually? Cobalt 3 chloride. Yes, it will be called cobalt 3 chloride. So the oxidation state of cobalt is +3 over here. Fine. I have the name written. It will come. The name will come in the slide. So I've erased that part. Let's try to solve the second one also. What are the ligands that we have? We've got a chlorido and we've got the ethane 1,2-diamine. Yes. So which one do we name first? E or C? C comes first, right? A, B, C, D, E. So C comes first. So the name will start with dichlorido bis ethane 1,2-diamine. Okay, dichlorido bis ethane 1,2-diamine platinum 2. Fine. So let me show you the names. Tetraamine chlorido nitrito N cobalt 3 chloride. And then we've got dichlorido bis ethane 1,2-diamine platinum 4 ion. Okay, why is that platinum 4? I said platinum 2 accidentally. Why is this platinum 4? Can we see? Pt Cl2 En2. Overall, we have 2 positive charge outside. So think, why is this a platinum 4? Because chloride ions are -1. Ethylene diamines don't have any oxidation state, 0. So you have 2 minus. Outside you have 2 plus, which means that platinum has to be 4 plus. So 4 plus minus 2 gives you 2 plus charge outside. And since there is no anion to stabilize it right now, this entire coordination sphere is a cation. We write the word ion at the end of the name. Shrivant, because the name has a di in it, right? Since the name of the ligand itself has a di, I use bis over here. I don't use diethane 1,2-diamine. That sounds weird. So we use bis ethane 1,2-diamine. Nanatsu, you don't need to write any statements. You simply write the answer and you will get the full marks. Alright, so let's see these. Try, please. So people who are asking, why did you write ion? Why did you write bis? I have explained that already, people. Did you join late? If you joined late, please join from beginning. Try this one, please. Pentamine nitrito O cobalt 3 ion. Do you realize the first entire species is ion over here? It has 2 positive outside, so it's an ion. It's not a neutral species, it's ion. So since this entire thing is ion, I will write ion next to the name. Yeah. Look at this case. What will we call it? Pentamine nitrito O cobalt 3 ion. Fine. What about the second case? K2NiCl4. What will we call this species? So potassium will come first. Potassium comes first, then the NiCl4. Potassium tetrachlorido. Should I write nickel or nickelate? Now, the potassium is the cation, the NiCl4 is the anion. Therefore, we will call it nickelate. What's the oxidation state of nickel over here, my dear friends? This is +2. So this entire thing has to be -2. Over here, essentially, we have NiCl4 with a -2 charge. Okay. So on chlorines, we have -1 charge each. -1 into 4 is -4. So out of -4, -2 is over here. So nickel should have +2. +2 minus 4 is equal to -2. So this is nickelate 2. Will we write iron? No. We won't write iron over here because this is not iron over here. This entire thing is a stabilized species. There is no charge separate. Yeah? So we will not write iron over here. In the first case, since we are writing only the iron part, we are not writing the anionic part, only the cationic part is written. That's why we will write iron. Fine. So these are the names, as you can see. Just have a look. Yeah, people who are asking 20, 20, 30, 30 times how is this called iron? People, what is iron? There's so many people asking why the first case is called an iron. What is iron? What's the definition of iron? Iron is a charged species. Could be a charged atom, could be a charged molecule. In the first case, this is a charged species, no? 2 positive charge. So the entire thing is an ion. Therefore, we write ion. In the second case, is there any separate ion? Cation and anion balance each other out. So is this entire thing ionic? Entire thing is neutral. So you don't write ion over here. Okay. That is why we write iron in the first case, because that is iron. Why would I call you human? Because you are hopefully human. Tejas, did you join the class late, bro? Yeah. People, please join the class on time. For cations and for neutral sides, we do not use 8. This is a cation, so we wrote cobalt. This is the anionic part, therefore we use nickelate. Okay. Charge -1, -1, -1 will be balanced by +3, that's all. Okay. So I was explaining why does this cobalt have +3 charge, because chlorine -1, chlorine -1, NO2 -1. So 3 minus balanced by 3 plus. All right. That's how it works. Fine. So people, that is your nomenclature revision. More questions you can do from the NCERT also. NCERT has lots of examples on nomenclature, lots of solved examples on nomenclature are also there in the NCERT. Let me show you where they are. So as you can see, look, so many examples you have. So look at these examples. The more examples you do, the more you'll understand how to name these particular coordination entities. Look at this one. Amine chloride nitrito N. So diamine chloride nitrito N platinum. What will be the charge on platinum? 1 Cl negative, 1 NO2 negative. 2. Diamine chlorido nitrito N platinum. 2. Do it this way. Revise from NCERT. Alright. Coolio. So, that was your nomenclature revision. My dear friends, once again, please let me tell you, this is a revision class. If you want to do from the very basics, 2 days later you have board exam. Today you want to do from basic. Congratulations. So let's move on to the next concept. So the next concept is about this idea that comes from the Werner's theory. Werner was the scientist who did these experiments. So my dear friends, when we look at this particular species, the part that is in square brackets is my coordination sphere. Alright. Whatever is outside is the counter ion. People, when we throw this in water, what will happen? I will get 2 chlorines because those chlorines are not a part of the coordination entity. They are outside the coordination entity. So you would get 2 chlorides and you would also get this entire cation. And you would get Ni, NH3, 6, 2 positive cation. So how many ions are produced in the solution from this complex? Total of 3 ions are produced. Total of 3 ions are produced. So the inside part does not break into smaller fragments. The inside species does not break into smaller fragments. That is the idea. So this is how it works. Right? So if I ask you, if I have a compound that looks like this, Ni, NH3, 4, Cl3. This is a different notation. I did not tell you what is coordination, what is not coordination. Think about it. This is a different type of notation. I have not told you if you have coordination sphere or not. Where is the coordination sphere? What are the ligands in the coordination sphere? You have to judge. So for this particular species, can you judge how many Cl negative are outside the coordination sphere? Can you judge how many chlorines are outside the coordination sphere? So what we need to do, we need to put 6 coordination number for our central metal over here. The nickel metal prefers to have coordination number 6. It wants 6 ligands around it. So if I have to keep 6 ligands, this type of a system makes sense. Yes? Do we understand? Since nickel wants 6 ligands, 4 amines will be ligands. Can amine be a counter ion? It can't be, right? Because amine does not have any charge on it. That is why amine has to be a ligand. If amine had a charge, then it could sit outside, but it doesn't have a charge. So forget about it. So amine sits inside, chloride sits inside, and 1 chlorine remains that sits outside. So you will have only 1 chlorine in this case, which is outside the coordination sphere. Very nice. Let's try this one now. When a coordination compound NiCl2.6H2O is mixed with AgNO3, 2 moles of AgCl are precipitated per mole of the compound. Write the structural formula of the complex, secondary valency of nickel in the complex, IUPAC name of the complex. Try. Can you tell me what is the complex? When NiCl2.6H2O, this is a different way of writing the complex. This is used with AgNO3. 2 moles of AgCl are precipitated per mole. what AgNO3 does is, so for every molecule of AgNO3, we need 1 mole of chloride ion. Okay. So it is saying that I have 2 moles of AgCl precipitating. Right? Acha. If I react this entire thing with AgNO3, if I react this entire thing with AgNO3, what will happen? How many moles of AgCl will be precipitated? X moles AgCl. Can you tell me how many moles of AgCl will this give me? I have only 1 chloride that is free. These chlorines are already bound to nickel. These are not free. There's only 1 chlorine that is free, and this free chloride will bind with the silver positive. So I will get only 1 mole of AgCl from this species. So if I'm getting 2 moles of AgCl, what should be the formula of the complex? The formula should be something like this: NiH2O 6Cl2. Very nice. So both of these chlorines can give you the 2 moles of AgCl precipitated per mole of the compound. Now, what is the secondary valency of nickel in the complex? What is the secondary valency of nickel in the complex? What do we mean by primary versus secondary valency? Yeah, let me remind you this idea. It's a weird idea. Let me remind you that idea from the NCERT. So if you search for primary, just a second. Primary valency, secondary valency was proposed by Alfred Werner. Weird concept, but let's understand. Werner proposed the term secondary valency for the number of groups bound directly to the metal ion. So basically, people, secondary valency equals coordination number. Okay, so let me put that idea over here in the slides also. That secondary valency is equal to coordination number. What is coordination number? If someone tells you define coordination number, how will you define? How will you define coordination number? Coordination number is defined as number of bonds metal has with ligands. It is not equal to number of ligands. No, that is an incorrect idea. It's not equal to number of ligands. It is equal to number of bonds the metal makes with ligands. Okay? Not number of ligands. Bonds that it makes with ligands. Yeah. For example, ethylene diamine is a bidentate ligand, right? Ethylene diamine is a bidentate ligand. So, for instance, let's think about this particular species, let's say. If you have this type of a coordination entity, then what's the coordination number of cobalt? The coordination number of cobalt is still equal to 6. Why? Because the compound looks something like this. It is still octahedral in nature. It has only 3 ligands around it, but the ligands are bidentate. Yeah, so you have one ethylene diamine on this side, another ethylene diamine on this side, another ethylene diamine on this side. So coordination number is the number of bonds the metal has with the ligands. Fine. So that is your secondary valency. So what's the secondary valency of nickel in this complex? 6. Okay. What is primary valency? What do we mean by primary valency? Primary valency simply equals oxidation state of central metal. The oxidation state, the charge of the central metal is known as the primary valency. So what is the charge over here? Nickel 2 positive. Why 2 positive? Because we have 2 chloride ions outside. Plus 2, minus 2, therefore neutral. So primary valency is 2. You will not write plus 2, primary valency is simply 2. Okay. What's the IUPAC name of this complex? Hexa aqua nickel 2 chloride. Hexa aqua nickel 2 chloride. 𝐂𝐻𝐿 is saying, sir, please increase the speed. What is the acronym complex? Hexa aqua nickel 2 chloride. That is very fast. Will you understand what I have for? Patience. If you want to watch this class faster, then once the live stream is over, you can watch it at 2x speed. Right? I'm limited by the fact that I am a human, can't go faster than a certain pace. So, in case you want to watch this class faster, you can watch it at 2x speed. That's absolutely fine. Later, obviously, once the live stream is over. Okay. So, my dear friends, we've revised certain ideas of the primary and secondary valency. We've revised what is coordination number. We've revised nomenclature. We've revised Werner's theory. Those ideas, very nice. So now, let us try to look at the valence bond theory. So, in valence bond theory, what we have is, we have hybridization. Yeah. In valence bond theory, we have hybridization. People who have joined late, please watch from the beginning of the class. So, write hybridization and magnetic character for the following complexes. First of all, let us look at NiCl4 2 negative. NiCl4 2 negative. People, can you tell me what is the oxidation state of nickel over here? Chlorine is minus 4 total. Out of that, minus 2 is outside, so nickel should have plus 2 oxidation state. So we have nickel plus 2. What is the electronic configuration of nickel plus 2? What is the electronic configuration of nickel plus 2? People, do you remember the entire transition metal series? I hope you do. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. Yeah. What are their atomic numbers? 21, 22, 23, 24, 25, 26, 7, 8, 9, and 30. So what is the electronic configuration of nickel? Nickel is 4s2 3d8. Can you see? 28, 4s2 3d8. Similarly, iron will be 4s2 3d6. Manganese will be 4s2 3d5. Chromium and copper, you know, are exceptions, but everything else can be written in this manner. So, nickel 2 positive will be a 3d8 type of species. So, if I want to draw this 3d8, what will the 3d8 look like? 1, 2, 3, 4, 5, 6, 7, and 8 electrons in the 3d orbitals. 2 unpaired electrons. Should I pair these? Should I be pairing these two electrons? I don't think we should be pairing these electrons. Why? Because chloride is a weak field ligand. We'll revise the spectrochemical series also. So, since chloride over here is a weak field ligand, we do not want to pair these. So, where will chloride go and sit? Chloride has to go and sit in the 4s and 4p orbitals, because this does not have any empty orbitals. My dear friends, do you realize that ligands are Lewis bases? What do we mean by Lewis base? Lewis base means electron pair donor. Every bond with ligand, basically ligand is giving 2 electrons into the metal. Every coordinate bond is formed by ligand giving 2 electrons into the metal. So I need 4 into 2, 8 electrons. I need space for 4 into 2, 8 electrons. So where will I put those 8 electrons? I'll mark over here. 1, 2, 3, 4, 5, 6, 7, 8. So all these blue colored X marks are electrons provided by chlorine. So since they are provided in 1s orbital and 3p orbitals, what will be the hybridization? sp3. For sp3 hybridization, remember what the shape is? Chemical bonding, 11th class. So for sp3 hybridization, the shape for this species will be tetrahedral. If you want to draw the diagram, it will look like this, exactly like your CH4 diagram. Chlorine, 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 chlorine. Overall, this guy has 2 negative charge. People, if you have to write the name of this species, what will be the name? The name will be tetrachlorido nickelate. Why did I write nickelate over here? Because overall this is a negatively charged species. So for overall anions, we put the word 8 at the end of the metal. Tetrachlorido nickelate 2. Since this entire thing is ionic, I will put the word ion at the end. Okay. All right. So, what about the next case, people? What about the next case? They ask you about the magnetic nature also. You have 2 unpaired electrons. So, unpaired electrons equals paramagnetic. Unpaired electrons equals to paramagnetic nature. Right? What is the formula for magnetic moment? Magnetic moment equals to root of n into n plus 2 Bohr magneton, where n is the number of unpaired electrons. So if you put 2 in this formula, you will get the magnetic moment of this compound. Okay. Fine. Next, let's look at CONH3 6 3 positive. Let us do that on the next page. We've got CONH3 6 3 positive. So people, over here amine doesn't have any charge, so you have cobalt 3 positive. What will be the electronic configuration of cobalt 3 positive? So this is a 4s2 3d7. If I remove 3 electrons from here, 1, 2 and 3, this will be a 3d6. So cobalt 3 positive is a 3d6 6 type of species. So let's make a normal 3d6 first. 1, 2, 3, 4, 5, and 6. But now, because amine is a strong field ligand, I will have to pair it. Pair because NH3 is a strong field ligand. So what will I do over here? 1, 2, 3, 4, 5, and 6. Now where do I have the spaces for my 6 ligands of amine? I need 6 into 2, 12 electrons. 12 electrons can be kept in 6 orbitals basically. 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. This is your 3D. This is your 4s. This is your 4p. Right? So what will the hybridization? D, D, S, P, P and P. D2sp3. This can be written as D2sp3. Inner D complex. I am using 3D. Inner D. If I used 4D, that would become outer D complex. This is an inner D complex. D2sp3 hybridization. And my dear friends, this is diamagnetic in nature. Right? This entire thing is diamagnetic in nature. Then the next thing that we have is FeF6 3 negative. Let's do it over there. FeF6 3 negative. What's the oxidation state of iron over here? We've got iron 3 positive, which is a D5 species, yes? Yes or no? D5 species, right? So what should be the do I have to pair it? No. Fluoride is a weak field ligand. So 5 electrons, you put them simply without pairing them. 1, 2, 3, 4, 5. And then the remaining spaces will be in the, 1 second. So this is your 3D, this is your 4S, this is your 4P, this is your 4D. So where do you have the spaces for those 6 fluorides? 1, 2, 3, 4, 5 and 6. So sp3d2. Now if they ask you about high spin, low spin, so many spins, so many unique electron spins over here, this is called a high spin complex. On the other side, however, we have pairing of all spin. There is no individual spin anymore. All the spins are paired, right? So these are low spin complexes. This is a low spin complex. What about this case? This is also called a high spin complex. Why high spin? Because 2 unpaired electrons are there. All right. Cool. So can you name these? Just for practice, can we name these? This will be hexamine, cobalt, 3 iron. What about this one? This will be hexafluorido, iron or ferrate. What will I call it? Will I call it iron or will I call it ferrate? That will be hexafluorido ferrate 3, because the oxidation state of iron is 3. So whenever we have anion 8 cation, simply put the metal name directly. Okay. So IV, both of these species will be octahedral complexes. Both of these will look something like this. Both of these are octahedral in nature. Yeah. So this one will be paramagnetic because we have unpaired electrons. This one will be, sorry, one second. This is the final case. Yeah. So no unpaired electrons. So this will be diamagnetic. Okay. Because there are no unpaired electrons anymore. Over here we've got so many unpaired electrons. So this would be paramagnetic. Diamagnetic, paramagnetic. Cool. Fine. Kishore Ram, did you join the class late? Please watch from the beginning. Alright, so that was the idea behind hybridization, magnetic character. Can we do this? I will teach spectrochemical series also, don't worry. Can you do this? Yes, Leo, thank you for the correction. Both of these cases are ions. This is also ion. Okay, what about this? So, carbonyl and cyanide both are strong field ligands, I am telling you. Now try. Using valence bond theory, predict the geometry and magnetic nature of NiCO4 and also of FeCN6, 3 negative. So people, what about the first case, NiCO4? Carbonyl is a neutral ligand. So nickel here is in the zero oxidation state. Now nickel is a 3D8 4S2, but this is in its ground state. Cobalt, sorry, I'm saying cobalt. Carbonyl, CO, not cobalt over here. Carbonyl, as I told you, is a strong field ligand. So what will happen is pairing will happen. How will this pairing happen? I will illustrate that for you. This is your 3D8 4S2 initially. These electrons are going to move inwards. The 4S2 electrons will be pushed inside. So after it gets bonded with the carbonyl, nickel will turn into a 3D10 species. 1, 2, 3, 4, 5, 6, 9 and 10. So nickel will turn into a 3D10 species after electrons are paired. So is there any space in the inner d orbitals? No, not anymore. The only space that we have remaining is in the 4s and 4p. I need 4 spaces for 4 ligands. So 1, 2, 3 and 4 sp3 hybridization. Pairing of electron is there. So this will also be diamagnetic. No unpaired electron, so this will be diamagnetic. And because this is sp3, what will be the shape? This will be tetrahedral in nature. Next one, will you do on your own? Hexacyanoferrate 3. Fe3 positive. Once again a D5 species. Yes. Can you try it on your own? Do it yourself. Okay. Because cyanide is a strong field ligand, you will pair electrons. And after pairing, you will get space in the inner D. Yeah. So D2sp3 this will be. Fine. So this is the idea. behind valence bond theory, how you draw these ideas. Pretty simple. Now, before we move on to the spectrochemical series separately, I will move to that, don't worry. Let us move towards isomerism. So what are the different types of isomerism that we have? Just a second. Yeah. Look at this. Dinesh, physical chemistry we'll do on Wednesday at 1 p.m. My dear friends, what are the different types of isomerism that we have? Let's revise isomerism. Isomerism is very important and also very simple. Let's revise those ideas from the NCERT. Then for isomerism, I'll show you very beautiful models, three-dimensional models for the complicated cases. Optical isomerism, etc. is difficult to visualize for coordination compounds, right? So I will definitely show you those cases also. Abhishek will come to that idea, bro. Don't worry. It is just a memory-based thing. We'll come to those ideas. So for isomerism, have a look. So isomerism in coordination compounds is of two types. Of course, you have your geometrical and optical isomerism. Of course, stereoisomerism, geometrical and optical isomerism is there. We'll do that. But first, we need to look at these cases. Structural isomerism. Fine. So first of all, we need to figure out structural isomerism. So there are four types of structural isomerism in coordination compounds. Okay. Linkage isomerism, coordination isomerism, ionization isomerism, and solvate isomerism. These are best understood via examples. So let's look at these examples now. First of all, let us look at linkage isomerism. Look at this. Linkage isomerism. Read. Linkage isomerism arises in a coordination compound containing ambidentate ligand. What is ambidentate ligand? Ambidentate ligand is when in one ligand it can bond from one side or the other side. You know one example. Nitrito N versus nitrito O. Ambidentate. Do you know the meaning of the word ambidextrous? Do you know the meaning of the word ambidextrous? Ambidextrous means someone who can use both hands with equal efficiency. Someone who can write with right hand also and left hand also. That's called ambidextrous. So ambidentate means it can use one atom for bonding, it can use some other atom for bonding also. Fine. So ambidentate ligand. Now, a simple example over here, another example is provided by the thiocyanate ligand, NCS negative, which may bind through the nitrogen to give metal NCS or through sulfur to give metal SCN. So the thiocyanate ligand also can bond via nitrogen or it can bond via sulfur. So this scientist Jorgensen discovered such behavior in the complex CONH3,5NO2Cl2. Okay, which is obtained as red form, which nitrite ligand is bound through oxygen, and yellow form in which nitrite ligand is bound through NO2. Understood? Did you understand what is going on over here? So this is one of the isomers. This is one linkage isomer. The other linkage isomer will look something like this. Cobalt, NH3, 5, ONO, Cl2. In one case, it is linked by nitrogen. In the other case, it is linked by oxygen. One of these is red in color, the other is yellow in color. Linkage isomer. Very simple. Yeah. Look at the example that's been provided here. Can we observe any linkage isomerism here? Are these two linkage isomers? This is not linkage isomerism, no? Do we have any linkage isomerism over here? No, in these examples, we don't have any linkage isomerism. Cool. Let's go back to the NCERT. That was your linkage isomerism case. Then let us look at this coordination isomerism. All right. Let's look at how to write coordination isomerism. Akshara, please watch the class from the beginning. We are already done with IUPAC nomenclature. Look at this. Coordination isomerism. This type of isomerism arises from the interchange of ligands between cationic and anionic entities. Just look at the examples, you'll understand this even better. Look at this example, CuNH36, CrCN6. If I replace the metals, I will get the coordination isomer. Can you see? Cobalt and chromium are replaced over here. Cobalt was with amine, now cobalt is with cyanide. Chromium was with cyanide, now chromium is with amine. So when we exchange these cases, that gives me coordination isomerism. Okay? Sham Sundar is asking, is this live? No, bro, this is not live. Dhanushri will look at specific examples where you need to count the number of isomers. Don't worry. Okay. Cool. Can you see this? Coordination isomerism. Santosh. Hey, let us complete at least 2 hours of class, no? Then we'll do a break. Yeah. Fun chat. All right. Coordination isomerism. I hope this is clear. Just exchange these two things. Coordination isomerism. Life is simple. Look at ionization isomerism. This form of isomerism arises when the counter ion in a complex solve itself is a potential ligand. So the ion can act as ligand and the ligand can act as ion. Look at this case. Sulfate goes outside, bromine goes inside, you get a different isomer. This is known as ionization isomer. Very simple. Put this inside, put this outside. Ionization isomer. This is the question that is being asked, right? This question, can you see? Ionization isomer. Sulfate inside, NO3 outside. Ionization isomer. This one also same thing. Bromine inside, sulfate outside. Ionization isomer. Yeah. So, this was the example of ionization isomerism. Then let's look at solvate isomerism. This is the interesting case. Okay. Solvate isomerism is slightly interesting. This is similar to ionization and isomerism, by the way. Let's have a look at this. This form of isomerism is known as hydrate isomerism in the case where water is involved as a solvent. So, broad name is solvate isomerism, but when water is used as the solvent, we call it hydrate isomerism also. It is very similar to ionization isomerism. Solvate isomer differs by whether or not a solvent molecule is directly bonded to the metal ion or merely present as free solvent molecule in the crystal lattice. Example will help us better. Example is this one. CrH2O6Cl3, which is violet in color. But if we have the isomer where inside I have only 5 H2Os, 1 chlorine and 1 H2O sits on the outside. My dear friends, what is this H2O doing outside? That H2O on the outside is known as the water of crystallization. and I will explain to you what water of crystallization is. Okay. So what is water of crystallization? We'll look at these examples also. This part of examples also good. But first, let me try to explain to you what is water of crystallization. Water of crystallization. Now, people, have you heard of this compound called blue vitriol? Have you heard of the compound called blue vitriol? You have heard of this compound yesterday in Felling's test and Benedict test. Yeah? Right? So, blue vitriol is basically CuSO4 dot 5H2O. Right? CuSO4 dot 5H2O. Now, this looks like this is sorry, it looks like it is dissolved in water, right? This thing is not dissolved in water. This is a crystal. Let me show you what it looks like. Then I will explain how water is inside the crystal only. Yeah. So let me show you. Looks like a very beautiful compound, by the way. It's a crystalline compound. This crystal has water inside it. All right. Blue vitriol. They are preparing it. Nice. So you can read more about it. If you break that crystal, this is what it looks like. Very beautiful looking compound. So now, how is water inside the crystal? See, the thing is, how does a crystal exist? Let me give you a very basic idea of how a crystal exists. Yeah. Let's say you have copper 2 positive ion. This is a positively charged sphere. This positively charged sphere will attract anions from all sides. So, sulfate ions will be attracted to it from all sides. SO4 2 negative, SO4 2 negative, SO4 2 negative, another, let's say, SO4 2 negative. This is a very simplified picture that I'm drawing for you. And around SO4 2 negatives, you will have more Cu2 positives because these are also negatively charged species. So you will have Cu2 positive here, Cu2 positive here, Cu2 positive here, Cu2 positive here. All coppers are 2 positive. Now, do you see that inside this arrangement, inside this lattice, this arrangement is called lattice. Can you see these gaps? These are known as interstitial gaps. My dear friends, what can happen is water molecules can go and sit inside these interstitial gaps. Water molecules can go and sit inside these interstitial gaps. So what happens is that these water molecules, they act like glue. These water molecules help everything stick together even better. So CuSO4 on its own is a crystal, but when you put water molecules, it becomes an even better crystal. Now, 𝐂𝐻 is asking, sir, why 5H2O? See, you can have different levels of hydration of CuSO4. You can have anhydrous CuSO4, which is white in color. Then CuSO4.5H2O can also exist. CuSO4.2H2O can exist. CuSO4.5H2O can exist. And this is very stable. Naturally, you can find this form of copper sulfate. Right? So, that is your water of crystallization. Now, looking at the example from the NCERT once again about our isomerism. Now, do you see the difference between these two? This one is a different compound, CrH2O6Cl3. The other compound is a different crystal, CrH2O5Cl, and in that you have one water of crystallization. This is not the coordination water. This is interstitial water. Nanatsu, think in terms of moles, not molecules. You can call it CuS, you can call it 2CuSO4.1H2O. Yeah. Okay. So let's look at these examples, people. Indicate the types of isomerism exhibited by the following complexes. What will be the isomerism exhibited by the first case? Can you tell? CrH2O2 C2O4 2. Can you think? What will be the kind of isomerism exhibited by this species? Achha, we might have some optical isomerism case also. Forget about the first two cases, those are from optical isomerism. Look at this case. First two cases are from optical, which we have not done. Look at this case. Can you see what is the kind of isomerism we'll have over here? NO3 can come inside, NO2 can go outside. So this can have your ionization isomerism. The remaining cases are from stereo. We'll do it in some time. This will give you the ionization isomerism. NO3 can go inside, NO2 can go outside. Very nice. Give evidence that these two are ionization isomers. Obviously, chlorine outside, sulfate inside. Ionization. Simple. No rocket science. So these were the 4 simple cases of structural isomerism. 4 very simple cases of structural isomerism. Now, let us focus our attention on the very interesting cases of stereoisomerism. Are you ready? Stereoisomerism is very interesting. Let us try to think about stereoisomerism. This will take a little time, people, but this will give you a very good understanding of stereoisomerism. First of all, let us look at geometrical isomerism. Let us look at the cases of geometrical isomerism that we need to discuss. Let us say, first of all, we have Ma2B2 type of square planar complex. Let's say we have a square planar complex where it has 2 ligands of one kind, 2 ligands of the other kind. So what is the kind of arrangement that I can have? Metal. On 2 sides we can have A, on the other side we can have B. So A and A are close to each other, B and B are close to each other. What could be the geometrical isomer of this case? The geometrical isomer could be A and A are opposite, B and B are opposite to each other. Yeah, these could be your 2 geometrical isomers. So people, the first one would be called the cis isomer, the other one would be called the trans isomer. Trans because B and B are opposite to each other, B and B are on the same side. Okay. Similar will happen when we have Ma2, B and C. If I have such a case, Ma2, B and C, if I have a square planar complex, so what will the 2 isomers look like? M, A, B and C. So in this case, A are close to each other. In the other case, let's put the A ligands opposite to each other. Fine. So A and A close to each other, this is the cis. A and A opposite to each other, this is the trans. These are the 2 cases. Okay. So this is geometrical isomerism. Ma2B2 square planar, Ma2BC square planar. One more case of this geometrical isomerism is MABCD, once again square planar. Can you think how many geometrical isomers this will give me? Can you think how many geometrical isomers we will get out of this? So M, A, B, C, D. Think about it. A opposite B, C opposite D. Let's make another isomer. M, A, C, B, D. Let's make another isomer M, A, D, B, and C. Can we have any more isomers over here? Can we have any more isomers? Think. I'll draw a structure. You tell me whether that is new or one of those structures only. Is this a new isomer? Do you realize this and this are the same? Can you see this and this are the same molecule? You take this molecule, rotate it like this. Same molecule. A and B are opposite to each other, no? You rotate it. Same molecule. Molecules are three-dimensional. It is our limitation that we have to draw them on paper. Otherwise, they are three-dimensional, right? And now, because visuals are better, I've brought my set of molecular models for you guys. So give me just a little while and I will make this for you. Okay. Let me make this even more obvious to you guys. By the time you can talk to me about something if you want. Let me find the... Yeah. Harita, it's okay. Because we want to avoid spammers, I will read the serious comments whenever they come. Hey, where are my octahedral molecules? Hold on, people. I've lost my... square planar species. I'm trying to find. Very good. Ah, got it. This one. This structure. Okay. You rotate it like this, you get this structure. Cool. So, yeah. So, you've got only 3 geometrical isomers over here and we can't name them cis and trans. Okay, these cannot be called cis and trans because how will you decide cis or trans? A opposite to B, opposite to A, CA opposite to D. You can't decide cis or trans over here. Cis or trans can be decided when you have 2 ligands of the same kind. 2 ligands same kind, same side cis, 2 ligands same kind, opposite trans. 2 ligands of the same kind at the same side cis, 2 ligands opposite of the same kind, trans. Okay, so we have 3 geometrical isomers over here. Pretty good, pretty simple, no problem whatsoever. Now, apart from these cases of geometrical isomerism, let us think about octahedral complexes and where they can show geometrical isomerism. So the first case of octahedral complexes where you can have geometrical isomerism is this one, MA4B2. I will draw the cases for you. So B and B are opposite to each other. This will be your trans isomer. And then the other one, M. So B and B are close to each other. The remaining parts are A. So this, since B are close to each other, this will be called the cis isomer. So whenever you have such a scenario, we've got cis and trans isomers. Okay, cis and trans isomers in this case. So, my dear friends, is any of these isomers optically active now? What do you think? Is any of these isomers optically active in nature? Unknown. You mean to say when are those compounds optically active? Without chiral carbon? Yeah, that is an advanced level concept, bro. Let's not go for it in the boards level class. So over here, can you guys tell me if we have optical isomerism in either of these cases? Are they optically active? Are they optically inactive? What do you think? Hey, this one has to be optically inactive. No, it's a symmetric structure. If I have a plane of symmetry in the middle, it is an achiral structure. So trans is definitely, trans structure in this case is definitely optically inactive. I have symmetry, plane of symmetry right through the middle of this structure. Plane of symmetry right through the middle of this structure, right? But what about the other scenario? What about this case? Will this be optically active? So Bhiksha, physical chemistry one shot will be tomorrow at 1 p.m. What about this? Are you saying it is optically active? Acha, if I show you plane of symmetry, it will be optically inactive, right? If there is a plane of symmetry, it will be optically inactive. Look, plane of symmetry is there, no? Cut it through the middle. Plane of symmetry. Yeah. Look at it from this side now. Cut it through the middle. Plane of symmetry. This molecule is symmetric. Left side is equal to right side. Symmetric molecules are not optically active. That's the point, right? Asymmetric molecules are optically active. Symmetric molecules are optically inactive. Since it is a symmetric molecule, it is optically inactive. So both of these cases over here are optically inactive. Both the cases over here are optically inactive. So Ma4B2, these are the examples. Then next, we have the most interesting case. Okay, this is the most misunderstood case, but this is the most interesting case also. Ma3B3. So let me draw the isomers for you, then I will show you in the models also what these isomers look like. So A all together, B and B all together. So B all together, A all together, and in the other case, what we will do is sorry, not this. Let's do this way. A and A opposite, and one A over here, B and B opposite, one B over here. Fine. These are the two different kinds of isomers that we have. Fine. So my dear friends, let's look at the first case over here. Can you see this is the representation of this one? Can you see? Red ones all A's together, black ones all B's together. Let me zoom into the camera a little and then I will show you what this looks like. Have a look. Okay. Can you see? All red ones together, all black ones together. So people, this type of an isomer, can you see a black face? This is a black face, right? On the other side, we have a red face. We have two different faces, right? A black face and a red face. So people, this particular type of isomer is known as the facial isomer. FAC. FAC. Facial isomer. The other side that we have, the other kind, let me make that for you. There we go. So now have a look. Can you see the red ones? A and A are opposite to each other. B. This is what we've drawn over here. Same thing. Cool. So, my dear friends, can you see a semicircle of black over here? In this structure, can we see a semicircle of black? Can we see another semicircle of red? Yeah. So, semicircle of black and semicircle of red. These semicircles are also known as meridians, right? You know, when you cut Earth into multiple segments, you call those meridians. So, those segments, semicircles, are meridians. So, this isomer will be called the meridional isomer, also abbreviated as MER. So, facial isomer, meridional isomer. Now, is any of these optically active in nature? If I show you plane of symmetry, it is optically inactive. Can we see plane of symmetry? Cut it from the middle, no? Symmetry. Left side equal to right side. Plane of symmetry. Right through the middle. Cut it from the middle. Plane of symmetry. This species is optically inactive. Look at this one. Look at the facial isomer. Can you see symmetry now? Right through the middle, can we see symmetry? Once again, right through the middle you cut it. Look at it from this direction. Left side equal to right side. Symmetric structure, this is also optically inactive. Yeah. So this structure is also optically inactive. So give me a second. Zooming out to normal view. So facial and meridional isomers both are optically inactive in nature. Fine. Next case. Now we have two very interesting cases. Okay. This is MEN2A2 type of species. Okay. So people, what is happening over here is we have a bidentate ligand in this particular case. Yeah. We have a bidentate ligand over here. So what is this going to look like? Metal. Let's take one scenario where A and A are opposite to each other. We have a bidentate ligand over here. We have another symmetric bidentate ligand over here. Okay, fine. Now, this isomer, since A and A are opposite to each other, will be called the trans isomer. Can you see this is optically inactive? Can you see this is a very symmetric structure, left side equal to right side? So, definitely, this is going to be optically inactive. Perfect. Now, what about a scenario where this is a cis case? So let's make one of the cis isomers of this species. Now, since ethylene diamine is a bidentate ligand, it is one ligand, right? Can I put ethylene diamine like this? I can't. Do you understand? I can't put ethylene diamine like this because it's not so long. Ethylene diamine is a small little ligand that can associate itself from two sides in one direction only. So I will have ethylene diamine over here and I'll have ethylene diamine over here. Now, people, does this look like an optically active species to you? Does this look like an optically active species? Can you tell? Think. This is the species that we have. Yeah. This is the species that we have. Can you find any symmetry? It's very weirdly asymmetric, right? Look at the direction in which these bidentate ligands are. You can't find any symmetry in this no matter where you look at it from. It's a very asymmetric kind of molecule. To verify, let me make the enantiomer for this case. Okay? So to verify the idea for you, let me also make the enantiomer for you. It will take just a minute to assemble the enantiomer. Working with these models takes a little time, but I'm sure those of you who are serious about studying this are patient enough to wait. Those of you who are impatient, you are free to do whatever you want. Okay. What else is going on in life, people? I hope all is good. Let me verify. Yeah, we've got mirror images. Can you see mirror images? Let me zoom in now and show you the magic of these mirror images. Yeah. Extreme zoom. My face will look super weird. Such high zoom, but yeah, there we are. Can you appreciate that these two are mirror images of each other? Yeah. Can we appreciate these two are mirror images of each other? Now, if these two mirror images do not superimpose on each other, they are optically active. Non-superimposable mirror images means optical activity. Let us try to superimpose the red things together. Red things are superimposed, red on red I've kept. Look at what happens to the black parts if I superimpose the red side. All pointing in different directions. No superposition. Yeah, can you see? If I try to superimpose the red parts, which I have successfully superimposed, look at what happens to the black parts. They're all pointing in such weird different directions. You can't even make sense of the structure anymore. Yeah. If I try to superimpose this black side, can you see this black side is superimposed? Can you see this particular black side is superimposed? But if I superimpose this black end, look at the other side. What is this jumble? These two, my dear friends, are asymmetric structures. These are non-superimposable mirror images. Yeah. These two are non-superimposable mirror images of each other. And that's why this particular compound is optically active. So that is why this particular compound is optically active in nature. optically active. So this is one of the cis isomers, and you will have its mirror image also, and that mirror image is going to look like this. And these two, how are they related to each other? These two are enantiomers of each other, people. These two are enantiomers of each other. Unknown in this case, mirror images will be superimposable because it's a symmetric structure. In this case, mirror images will be non-superimposable because these are asymmetric structures. Gautam Shri, it's okay. Some devices don't support zoom function. For instance, if someone is looking at it in the laptop, then zooming is a little difficult scenario, but it's okay. You will understand it. Julio. So, trans is optically inactive while cis is optically active. And this question was asked in previous years also. Look at this one. This is a CBSE board question. This will come for 3-4 marks easily. So, draw the geometrical isomers of COEN2 Cl2 positive. And which geometrical isomer of COEN2 Cl2 positive is not optically active and why? So, how will you write this? You will basically make these three structures. Where did it go? Just a second, people. Lost that page. Yeah. You will make these three structures. Instead of A, you will make the chlorines. Yeah. So instead of A over there, chlorines are given. So you will write these three structures and you will say that the trans structure is optically inactive because it has a plane of symmetry in the middle. This is a symmetric structure. Its mirror image is superimposable on this and therefore it is optically inactive. Symmetric structure has a plane of symmetry. Mirror images are superimposable, optically inactive. Asymmetric structures, mirror images are non-superimposable on each other, optically active. So this is the same question asked from board exam. Okay, one more case is remaining, people, for optical activity. One more optical active case which is important for you is this one. MEN3. I'll draw the structure of this for you and then I will show you the models as well. And you would be surprised to know that this is optically active. It doesn't look like it, right? The structure looks very simple, looks very, how do you say, innocent, for the lack of better words. But it is optically active in nature. Let me show you the models. So this is one of the isomers. Let me make the other one as well, the mirror image. Okay, almost there. Have you ever seen these models before in any class online? Can you see? Two mirror images. Yeah. So we've got two mirror images over here. If they superimpose, they are optically inactive. If they don't superimpose, they are optically active in nature. Let's try to superimpose them. Let's try to superimpose the ends that I have in my hands right now. These two ends. Let's try to superimpose that part. So this top part is superimposed. Can you see this part is very nicely superimposed, black on black, black on black, nice. Look at the chaos on the other side. Look at the chaos on the other side. Let me show it to you on a white background. I think that'll look a little better perhaps. Gautam Shri, I will try to do that. The problem with it is that there are too many spammers in the chat. Yeah, okay, whatever. Now see. Mirror images superimposed from this side. Look at the other end. What chaos is this? No superposition. Yeah. If you superimpose one of the sides, all the other things are non-superimposable, pointing in different directions altogether. So people, two non-superimposable mirror images, and therefore this compound is optically active in nature. That's the beauty. This is optically active. Nice. Let's make the enantiomer as well. Metal. So En over here, En over here, and another ethylene diamine over here. These two are your enantiomers. Very nice. Perfecto. So these are your cases of geometrical and optical isomers that you need to keep in your mind. All of them drawn on the screen. All of them shown with models also. Nice. So this is done. Can you do this? Draw the geometrical isomers of PtCl2 En2 2 positive ion. Same thing. Yeah, same thing. Trans is optically inactive, cis is optically active for this particular case. Yeah. Name the type of isomerism when ambidentate ligands are attached to central metal ion. Give one example of ambidentate ligand. So people, what is this one called? This one is called linkage isomerism. Yes. So the example, as we have seen, NO2 ONO. So nitrito ligand is an example of an ambidentate ligand. One more example that you can give is metal SCN versus metal NCS. Thiocyanato is also an ambidentate ligand. Very nice. So good stuff. This is done. This is done. Okay, we'll do this. We'll do this also. Fine. So I think isomerism previous year questions, you understand how they will be asked. These are the kind of questions you will have from isomerism. Nice. Isomerism is revised, covered, all cases seen. So now the next thing that we're going to do is we're going to look at the spectrochemical series. Okay. Now we have to do the spectrochemical series. Yeah. So people, what is the spectrochemical series? This idea comes from crystal field theory. All right. Now, let's read a little bit about the crystal field theory, and then I'll give you ideas of how it exactly works, how are normal levels of d orbitals split into two different levels, separate for octahedral, separate for tetrahedral, and we will then solve questions related to crystal field theory. Okay, so crystal field theory explanation and everything should take another half an hour. So half an hour, this chapter will be completed. After that half an hour, we will move on to DNF block elements. DNF block elements is a smaller chapter that will not take more than 2 hours. So this class, 2.5 hours more. So after crystal field theory explanation, we can take a break. Fine. All right. The crystal field theory is an electrostatic model. First limitation of the crystal field theory over here. First limitation of the crystal field theory. It is an electrostatic model which considers the metal ligand bond to be ionic. Till now, we've been making models. We've been saying there are so many beautiful covalent bonds, coordination bonds, wow. And now suddenly crystal field theory says, I don't care, ionic bond. Yeah. So, crystal field theory is an electrostatic model which considers metal ligand bonds to be ionic, arising purely from electrostatic interactions between the metal ion and the ligand. Purely positive negative attraction. Ligands are treated as point charges in case of anions or point dipoles in case of neutral molecules. The 5d orbitals in an isolated gaseous metal atom or ion have the same energy. Do you understand that the 5 orbitals that we have in the d subshell, all of them will have the same energy? So, this is how we draw them. Can you name these? D x square minus y square, d z square, dxy, dyz, and dzx. These 5 orbitals in the absence of any electric field are degenerate to each other. In the absence of any electric field, these orbitals are degenerate. They are all of the same energy. Fine. All right. Now what happens is, when ligands approach the metal, this degeneracy is maintained if a spherically symmetric field of negative charge surrounds the metal. However, when this negative field is due to ligand, in a complex, it becomes asymmetrical and the degeneracy of d orbitals is lifted. This results in splitting of the orbitals. The pattern of splitting depends on the nature of the crystal field. Let us understand crystal field splitting in the different crystals. So first of all, do we understand what's going on? Originally, all the d orbitals were degenerate. All of them had same energy. But now ligands will approach. So when ligands approach these d orbitals, their energies will be changing. Their energies will become different. My dear friends, what happens when I bring an electron close to another electron? When I bring two negatively charged species together, what's going to happen? There is going to be repulsion over here. Yes. There's going to be a good amount of repulsion in this scenario. Very nice. We understand that. Now, imagine the formation of an octahedral ligand. Imagine the formation of an octahedral ligand. This is how we are drawing it. People, can I say that this, let's say, is the z-axis? Can I say this is the z-axis? I can say, right? Can I say this is the x-axis? This is the y-axis? Can you understand that the octahedral species can be imagined as if one of these lines is on the z-axis, one of these lines is on the y-axis, one of these lines is on the x-axis. So, people, what is happening when we make an octahedral complex is that the ligand's electrons, okay, this Li is not lithium, this Li stands for ligand, okay, I'll just use L. Why use Li? Use L. So, ligands are approaching from y-axis, x-axis and z-axis directly, right? Now, which orbitals out of these 5 are on the axis? People, can you tell? Out of these 5 orbitals, which of these are on the axis? This is on z axis. This one is on the x and y axis. And these 3 are between axes. They don't lie on top of the axis. They are at 45-degree angles from the axis, and I will show you those images also. But these 2 orbitals are on the axis. So now what's going to happen is, because these are on the axis and the ligand is approaching from the axis, the electrons in these orbitals will face repulsion. Electrons in these orbitals face repulsion, implies their energy is increased. So their energies are increased. And since they are away from the ligands, their energies will decrease. Okay? So that's how it works over here. Energies in these orbitals that are along the axis, it increases, and the energies of the axis that are, of the orbitals that are not along the axis, that energy decreases. So let me show you, there was a very good diagram that we had. Field splitting. Give me 1 or 2 minutes, people, to find out that web page that I'm trying to look for. Yeah, this one. This is a very beautiful website that we have called Chem Libre Texts. Beautiful website. And this shows you the same ideas that I've just tried to explain. Yeah. So, as you can see, octahedral species, ligands come from the axis, so the energy of the dx square minus y square and z square is lifted, and the energies of xy, xz and yz are reduced. Overall energy remains conserved. So if I add these energies together, overall the energy remains conserved. Fine. So, showing you the diagrams of the d orbitals. Look. So this is your dx square minus y square. It lies along the xy axis. Yeah. Just see. This lies along the xy axis. Dx square minus y square. Look at the dz square. This orbital lies along the z axis. So these energies become higher. And look at the remaining cases. Can you see? Just focus on one of these. Can you see the orbitals are between the axis, not on top of the axis? So ligand is approaching from here, but the orbital is pointing in some other direction. So this does not face that repulsion, and therefore these energies are lowered. Very nice. So this is why the splitting happens in this particular fashion. Right. So now you understand how the splitting happens in crystal field theory. So because of the approach of ligands, your degenerate 5 orbitals, they split into different levels. Dx square minus y square and dz square on the top, xy, yz, zx at the bottom. My dear friends, this central line is known as the barycenter. Okay, this central line is known as the barycenter. Now, energies at the top will have a plus sign next to them. Energies at the bottom will have a minus sign next to them. At the top, you will give it how much energy? For each orbital, for each electron in these orbitals, what will be the energy? Can anyone tell me? Plus 3 by 5 delta octahedral. Delta stands for splitting. O stands for octahedral. And at the bottom it will be minus 2 by 5 delta octahedral each. Plus 3 by 5 delta octahedral each. Minus 2 by 5 delta octahedral each. Why 3 by 5, 2 by 5? See, total levels are 5. Now, energy of the top levels will be 2 into plus 3 by 5. Energy of the bottom levels will be 3 into minus 2 by 5. Total energy is conserved. Total energy is conserved, right? So, people, this is how the crystal field splitting works. Okay. This is how the splitting happens in octahedral cases. The above two levels are known as the Eg levels, and the bottom three levels are known as the T2G levels. E stands for a doubly degenerate system. Doubly degenerate means two orbitals of the same energy. T stands for triply degenerate system. T2 stands for a triply degenerate system. So you have three orbitals of same energy. So E and T2 stand for their energy. G stands for Girardet. G stands for Girardet. And Girardet basically means center of symmetry. This is a little advanced information that I'm throwing at you. Center of symmetry. People, do you realize that the octahedral species has a center of symmetry? Diagonally opposite ends are similar to each other. This end is similar to this end. This end is similar to this end. This end is similar to this end. So the metal can be thought of as a center of symmetry over here. So for octahedral cases, since center of symmetry exists, we put the word Girardet in both of these cases. Okay, perfect. Now, the idea is that this splitting between the energy levels is caused by ligands. More splitting implies we have a strong field ligand. Okay, and less splitting implies that we have a weak field ligand. That's the idea. More splitting is done by strong field ligands, less splitting is done by weak field ligands. And now, the sad part about this theory, is it does not explain which ligands are strong, which ligands are weak. It just gives you an order by doing some experiments. So crystal field theory does not explain the strength of ligands. It just gives you a series to remember. It's a memory-based thing, sadly. The strengths of ligands are explained in ligand field theory, which is not in our syllabus. Crystal field theory only just gives us this. It just gives us something to remember, something to memorize. So iodide is the weakest over here. And then we keep going, and carbonyl is the strongest ligand over here. Okay, so this is the series that you have to remember, unfortunately. Kichu, I will give you 10 or 15 minutes for the break, don't worry. So, the idea is that this is where we draw the line for strong versus weak field ligands. That's where we draw the line. So over here, all the ligands that we have are strong field ligands, and below this, what we have are weak field ligands. There is one or two exceptions where water acts as strong field ligand, but those exceptions will do for JEE, not for boards. So after water, strong field ligands, water and below, weak field ligands. So please keep this series in your mind if you can. No one will ask you to write the entire series. Yeah. No one's going to ask you to write down the entire series. But okay, if you can memorize, it's better, especially for JEE exam. Yeah. So Madesh is asking, is oxalato a strong or a weak field ligand? It is a weak field ligand, bro. Prajesh, yeah, that is true. Sometimes oxalate might act as a strong field ligand. So that happens in very specific cases, which we'll do for JEE. For boards, we don't need to worry about those cases right now. Darshini is saying, is there any trick to remember? Darshini, there's no trick to remember the exact order. However, you notice the pattern. You have halogens over here, sulfur and halogens. Then you have oxygen. And then when nitrogen acts as the bonding species, that is where the ligands are strongest. So nitrogenous species are strong, oxygen species are weaker, and then you have halogens and sulfur. The exception over here, I mean the weird one, being the carbonyl. Carbonyl is the strongest field ligand. So that's just a pattern, right? Study Hard is asking, why is CO the strongest? Because of its synergic bonding aspects. But anyway, no one's going to ask you about that idea. Yeah. So this is what we saw from in the NCERT. It's a little low quality diagram, but we saw this on a better website. Spectrochemical series, great stuff. Okay, so let's solve a couple of questions from the board exam previous years to see how we can apply these ideas. Okay, this one is done. Let's do this. Using crystal field theory, write the electronic configuration of D5 ion if splitting is more than pairing energy. Okay, so what do we mean? This is your splitting energy. This is your pairing energy. Let's try to figure out this case. While writing these down, you will understand more information. So, what is pairing energy? Pairing energy is the energy required to pair two electrons. Splitting energy is the splitting that happens. Over here, splitting is a lot, pairing energy is lesser. Too much splitting, pairing is easy. How do we read this statement? We read this statement as electron pairing is easy, splitting is too much. Yeah, there is too much splitting that is happening, so pairing electrons is easy. What does this mean? If there is too much splitting, it essentially means we have a strong field ligand. Yeah, that's what it means, right? It means we have a strong field ligand over here. So, O stands for octahedral. In octahedral cases, above 2 levels are your Eg levels, the bottom 3 levels are your T2G levels. There is too much splitting over here. So what you will do is, all the 5 electrons you will put in the lower level itself. 1, 2, 3, 4 and 5. Pairing is easy, splitting is difficult. Pairing is easy, splitting is too much, so pairing will happen. So what is the final electronic configuration that you will write over here? You will write T2G5Eg0. What will be the final crystal field stabilizing energy? CFSE stands for crystal field stabilizing energy. This will be equal to 5 electrons into minus 2 by 5 each plus 0 electrons into plus 3 by 5 each. Yes. Remember, the top levels have plus 3 by 5 each and the bottom levels have minus 2 by 5 energy each. So 5 electrons into minus 2 by 5 plus 0 electrons into plus 3 by 5. So this comes out to be how much? Minus 2 times splitting energy octahedral minus 2 times splitting energy octahedral. So since minus sign is there at the end, minus means energy will be released. Exothermic process, stabilization. Okay. Pranav, so over here it says 0. This O stands for octahedral. That is how we understand this is octahedral. Okay. So if you have 6 ligands, if the coordination number is 6, octahedral species. If the coordination number is 4, then you will have mostly tetrahedral species. Okay. Unknown, we would consider that, but not for board exams once again. Not necessary. Okay. What about this case? On the basis of crystal field theory, write the electronic configuration for D4 ion where delta octahedral is less than pairing. So over here, splitting is less, pairing is difficult. This is a weak field ligand case. The splitting is not much between the energy levels. So 4 electrons, 1, 2, 3, 4. Pairing is difficult, splitting is very less. So the final configuration becomes T2G3 Eg1. What will be the final CFSE? CFSE will be equal to 3 into minus 2 by 5 plus 1 into plus 3 by 5 into delta octahedral. That's it. Over here there are a lot of electrons individual. So this will be called a high spin complex. The previous case, since spins are paired with each other, you are forcing them to get paired. This will be called a low spin complex. High spin, low spin. Nice. Very simple. Once you understand the crux of it all, it turns into a very simple idea. Okay, let me see. Let's do this one. Can you explain the reason for this? EVA, yes. Diamagnetic complexes are low spin complexes because everything is paired. Yeah. So people, we can explain this, right? We can explain this via their electronic configuration. The first case will be CO NH3 6 3 positive, where this is a cobalt plus 3. So CO plus 3 will have electronic configuration of D6, right? Fine. So since it is a D6, if you want to draw the Eg T2G levels, this is what it will look like. And if you want to draw the hybridization aspect, you can draw it like this. So you've got 1, 2, 3, 4, 5, 6. And where do we put the amines? 1, 2, 3, 4, 5, and 6. D2sp3. So amine, being a strong field ligand, can pair all the electrons, creating space in the inner d orbitals. At the same time, over here, you have only nickel 2 positive. Ni2 positive is an outer orbital complex. Why is that an outer orbital complex, people? Because inner d does not have space only. Yeah. Because in the second case, inner d, you don't have space for so many amines. Let us try to make that also. I have NiNH3 6 2 positive. Let's make it over here. So NiNH3 6 2 positive. So how will we explain this idea? We can explain this by VBT only. No need to make crystal field theory in these cases for board exams. So Ni2 positive is a 3D8 species. So what we can draw over here is this is the ground state. If I cause pairing, let's say we do pairing. Let's say we do pairing. Now where is the space for 6 amines? The space for 6 amines, this is your 4s, this is your 4p, this is your 4d, and this is your 3d. If I try to find for 6 spaces for amines, I can have 1, 2, 3, 4, 5, and 6. But what is this? This is a DSP3D. Have you ever heard of this type of hybridization? Have you ever heard of DSP3D? Nah. DSP3D is not possible. Why? Because this orbital's energy is very different from this orbital's energy. They can't be hybridized together. For hybrid orbitals, you need orbitals of similar energies. These two are too different in energy. So you can't use this. You just cannot use this for your benefit. You will have to use the outer D. So the reason why this is an outer orbital complex is there is not enough space in the inner d orbitals. There is not enough space in the inner d orbitals. Okay. Gautam Shri, the simple idea is there is not enough space in the inner d orbitals, so you have to use the outer d orbitals for hybridization in NiNH3 6 2 positive. All right. So now that we have done, hold on. Now that we've done the crystal field theory for octahedral complexes, let us also think about the crystal field theory for tetrahedral complexes. Yeah, octahedral complexes, we understand how it works. What about tetrahedral complexes? What about the splitting in tetrahedral complexes? My dear friends, what happens in tetrahedral complexes is, think about a tetrahedral molecule. Ligand, 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 ligand. Now the idea is that in this particular structure, none of the ligands are on any axis. None of the ligands are on any axis. I'll show you that 3D diagram also. So over here, ligands are between axes. They're not on any axis. Why was splitting happening earlier in octahedral case? Because ligands were coming right on top of the axis where you had orbitals. Now ligands are not on any axis. Yeah, ligands are somewhere in the middle of the axis. So let me show you that diagram also. Look at this case. So where are the axes? Let me draw the axis in blue color for you. I'll highlight the axis in blue color. So this is your axis. This is your axis. And this is your axis. This is your Z, X and Y. But now where are the ligands? This is where your ligand is. This is where your ligands are. So ligands are not along the axis anymore. Which orbitals are in between the axis? Which orbitals are between the axis? Showed you just a little while back. XY, YZ and ZX are in between the axis. So in the case of tetrahedral, XY, YZ, ZX, these are between the axis. So these will interact more with ligands, these will be repelled more by ligands. So that is why these are now higher in energy for tetrahedral complexes. Because the ligands are close to these three, these will become higher in energy. This is how the splitting for tetrahedral looks like. XY, YZ, ZX on the top, x square minus y square, z square at the bottom. Alright, so that's how it's going to work. Just a second. Yeah. Cool. So the above level is called the T2 level, the bottom level is called the E level. Why don't we use G over here? Why don't we use Girardet over here, people? Why not G? Because there is no center of symmetry in tetrahedral molecules. Center of symmetry means opposite ends have to be the same. So octahedral molecules, opposite ends are similar. But tetrahedral molecules, there is no diagonally opposite end, right? Look at this tetrahedral molecule. Is there anything diagonally opposite? No, nothing. There is no center of symmetry over here because diagonally opposite ends are not similar. So that's why we don't use the G suffix for these. So it is observed that for octahedral the splitting is usually higher than tetrahedral. In tetrahedral complexes splitting is very less. So in tetrahedral complexes splitting is much lesser than octahedral. Can anyone explain why? Can you think why this is the case? In tetrahedral, the splitting is very less. In octahedral, the splitting is quite a lot. So we can approximate that for the same type of ligand and metal, the tetrahedral splitting is somewhere around half of the octahedral splitting. Tetrahedral is 4 by 9 times octahedral splitting for same type of metal and ligand. Why so? Can we think why? Think about the ligand versus orbital interaction. Think about the ligand versus orbital interaction. If you think about the ligand versus orbital interaction, you will be able to understand that idea. I'll try to give you that visualization. So people, in the case of an octahedral complex, these are the axes, x, y and z axis. Ligands are on the axis. These are the orbitals. Let's say my finger is the orbital. This is the ligand. There is a perfect head-on repulsion over here. Head-on repulsion. Yeah. Proper head-on repulsion is happening over here. So these are where my orbitals are. Now in the tetrahedral case, the orbital is here, the ligand is somewhere here. There is no head-on interaction of the ligands versus orbitals. Even in the orbitals that are close to the ligands, the interaction is not head-on, it is slightly sideways. So in tetrahedral, the interactions of orbitals with ligands are not head-on. And that is why you have lesser splitting. That is why you have lesser splitting, and because splitting is so less, you can explain this observation also. Why are low spin tetrahedral complexes not formed? Can you try to put it in your words? Can you try to put it in words, people? Why are low spin tetrahedral complexes not formed? Low spin tetrahedral complexes are not formed because splitting is very less for tetrahedral complexes, delta T will always be less than pairing. So always pairing electrons will be difficult. So you will always make high spin complexes for tetrahedral. Yeah, always 1, 2, 3, 4, 5. This. You don't do pairing over here because it is easier to go to the higher level than pair it. Julio, very nice. So that was about your crystal field theory, octahedral splitting, tetrahedral splitting. We did some examples. We did some questions that came from this theory in the previous years in board exams. Very nice. Now one more question and then we will wrap coordination compounds. I will give you a break, okay? People, just little bit. See, we have board exam in 2 days. So we need to build our stamina, right? Board exam itself is of 3 hours. 3 hours at a stretch, you should ideally be able to study. I know you are tired. I will give you a break after this particular question. After this question, people, out of FeNH36 3 positive and FeC2O4 3 negative, which complex is more stable and why? So this is also a previous year question. Shubin, this is one of the important questions, bro. All the questions that we are doing today are previous year questions, important board questions. So this one will be your typical octahedral species. Fine. But on the other hand, your C2O4 is a bidentate ligand. What does C2O4 look like? C2O4 looks like this. Oxalato, bidentate ligand. So what is this complex going to look like? This complex will look a little more fancy because it has your bidentate ligands. Fine. Now, people, this complex that we have formed is known as a chelate complex. Whenever a ligand forms a ring with the metal, this ring formation is known as chelation. And since in a ring formation, the ligand is bound to the metal multiple times, this bond is stronger. You have multiple bondings, right? Imagine if I'm holding this bottle with one hand, you can snatch it away. But if I'm holding this bottle with two hands, now you can't snatch it away, right? So because there is more bonding with the metal of one same ligand, these complexes are more stable. So chelate complexes are found to be much more stable. So this one is the more stable complex. All right. So let me give you some background of whatever is. Look at this. When a di or a polydentate ligand uses two or more donor atoms simultaneously means at the same time, to bind to a single metal ion, it is said to be a chelate ligand. Okay. Such complexes called chelate complexes tend to be more stable than the similar complexes containing unidentate ligands. Okay. So whatever I wrote on that question is exactly what is mentioned in the NCERT for chelate complexes. Okay. Very nice. So one more question. The question for chelate complexes can be asked in this manner, or it can be asked in this manner. Yeah. So which of these is more stable? Or they can ask you, why are chelate complexes more stable? Chelate complexes are more stable because one ligand makes multiple bonds with the metal, forming a very stable ring. You can draw such a complex, you will get full marks. So both of these are board previous year questions. They can ask this way, they can also ask this way. Chelation. So now, technically our coordination compounds chapter is over. Coordination compounds chapter is over. Up next, we will be doing D and F block. So coordination compounds, what you guys need to do after this class is go through the NCERT once. If you go through the NCERT and solve all the questions of the NCERT board examination, definitely you'll get full marks. Okay. Now, up next will be D and F block. So we can do a little bit of a break. If you want a break, we'll do 5-6 minutes of a break. All right. Madesh, think about the magnetic property from valence bond theory. NH3 is your strong field ligand. Oxalato is your weak field ligand. So think about the magnetic property. NH3 case will be low spin. Oxalato case will be high spin. So think about the electronic configuration of iron and see if pairing causes 0 unpaired electrons or not. Think about it, bro. Okay. Acha, people, before I give you this break, just random information that I want to throw at you. Have you heard of this disease called hemochromatosis? I'm not sure of the exact spelling, but have you heard of this disease called hemochromatosis? What happens in hemochromatosis is that your body starts to accumulate a lot of iron. Very nice. Some of you know. Your body starts to accumulate a lot of iron. Your body is not able to process iron in it. So, in these heavy metal poisoning diseases, yeah, if you get lead poisoning, let's say, if you get heavy metals like iron depositing in your body, if you have excess of copper inside your body, how do we get rid of these heavy metals? What we do is we ingest medicine that has a ligand that can chelate with the extra iron inside the blood. So this extra iron inside the blood, we will throw ligands inside our body. Those ligands will create chelate complexes with iron. Since these complexes are so stable, our body will not be able to use them up anymore, and these can be taken out. Chelation therapy. So chelation is used to cure such diseases where you get heavy metal excess inside the body. Very interesting thing. So, Kevin, yeah, sure, man. All right, so up next, we're going to have D and F block. So around 5 minutes of break, approximate 5 minutes. Call it 7 minutes. May also become 10 minutes, but we'll take a small break now. And after that, we'll come and talk about the D and F block elements. Fine. Okay. See, I cannot play copyrighted songs, so I will play the only copyright-free song that I have. Please bear with it. Hello, check. Alrighty, people. What's up? How's life? D and F block elements. Very weird chapter, honestly. So purely memory-based chapters. D and F block elements. Yeah. So before we get to that chapter, let's have a small chit chat. And let me tell you one thing. The best way to study inorganic chemistry is always to look at questions and then find the theory behind those questions. Usually what we try to do for inorganic chemistry and chemistry in general is that first we try to complete all the theory, and then we move to questions. But then we are like, we know all the theory, but why can't I solve questions? Inorganic chemistry especially, it's always better to look at questions and then try to find the theory behind that question. Now, since your exams come from the NCERT textbook, it is very easy to find the answer to questions. So look at a question, try to find the answer in NCERT, look at a question, try to find the answer in NCERT. So that is exactly what we will do for the DNF block chapter. And in that process, we'll revise a whole lot of things for that chapter. Yeah, cool. So Subin is saying important questions. Bro, simply search for CBSE previous year questions on Google and you will find multiple websites with really nice segmentation of those questions. Chapter wise also you will get. Emperor Nobilius. I'm not sure if I understand. Okay, cool. Lok Pradeep, so unfortunately I have to keep the slow mode turned on because when I turn the slow mode off, there are some people who wreak havoc in the chat box and turn Master Tamil into Master Tinder. That's what I don't want. Judy, I know it's been more than 5 minutes. I write 5 minutes over here because if I write 15 minutes over here, then live chat will become, live students will go away. So to keep people live, I write 5 minutes. Otherwise, everyone will be like, okay, we'll come after 10 minutes, and no one comes after 10 minutes. Sasi, so board previous year questions are the ones that we are doing today. All the questions that we did were all board previous year questions. Ramesh, unfortunately, I don't know how to. I will learn slowly. If I keep teaching you guys, then I can teach you English and chemistry. You guys can teach me Tamil. Yeah. So I will also learn from you. Where are you guys from? Just curious. The live students. Which city? I'm not asking about state. State mostly Tamil Nadu, I know. So which city are you guys from? Alone King, thank you. Very nice. Harish, we are neighbors, man. I'm in Bengaluru. Coimbatore, Chennai. Very nice. We got people from Kanyakumari also. I've been to Kanyakumari, by the way. I've been to Chennai also. Pondicherry also, we have in the chat. Kumbakonam. Reminds me of coffee. Madurai. Very nice, people. I like it. Trichy. Tanjore. Salem. Perfect. One of my favorite roads to travel on is the Bangalore-Salem, the Salem-Kochi highway, and then that Salem highway extends to Bengaluru also. That's one of my favorite roads to travel. Such beautiful highway, man. I've done that highway so many times. Coimbatore people also there, very nice. No one from Nilgiris. No one from Kunur. Harish, yeah, in all my automobiles, I've done that, man. So in my Ducati, I have 3 motorcycles and 1 car. So I've taken all of them on those roads. Yeah. So I've done a lot of roads in Tamil Nadu. I have been to Obviously, Kanyakumari I've been to. I've been to Pondicherry. I've been to Ooty, Kottagiri, Kunur, that area, Nilgiris. Yeah. And I've been to Chennai also. And then I keep riding to Shulagiri, Krishnagiri because they are very close to Bengaluru. Yeah. So, Vellore also once I've crossed while going towards Chennai. These roads I keep traveling. Salem also I've crossed multiple times while going towards Ooty only. So, love those roads. I personally believe, so I've traveled all across the country on my motorcycle. On my motorcycles, I've traveled all across the country, and I personally believe that Tamil Nadu has the best roads in the country. Literally, the most smooth, enjoyable roads are there in Tamil Nadu, for sure. Yeah. Amy is from Ooty, very nice. Especially if you go from that one of my favorite roads in the country is when you go from Mettupalayam to Kottagiri to Ooty. I wish I could go there every single day. Mohammed Rizwan, that is true for every city in the country, man. So we can't do anything about it. If we come to the highways, and even a lot of state highways are very good in Tamil Nadu. Some are in bad condition, I know, but it's okay. Chalo, let's come to the D and F block elements. We'll talk about travel and roads and stuff later. So people, as I said, we'll target revision via questions in this chapter as well. So let us look at this particular question. Account for the following. Please explain these ideas. Why do transition metals and their compounds show catalytic activities? Why are zinc, cadmium and mercury called non-transition elements? Why are zirconium and hafnium of almost identical atomic radius? So now, if you know these, great. But what if you want to revise them from scratch? How do we figure out transition metals and their catalytic activities? How do you account for it? So what you simply do is you open the NCERT of this chapter. You do the Control F and you search for catalytic. The transition metals and their compounds also exhibit catalytic property and paramagnetic behavior. So what is mentioned about their catalytic activity? Have a look. Transition metals and their compounds are known for the catalytic activity. Okay, understood. This activity is ascribed or attributed to their ability to adopt multiple oxidation states and form complexes. So what will be the reason for that answer? The question that we had on the screen. Here, just a second. Now have a look. So what would be the main reason? The ability to adopt multiple oxidation states and to form complexes. If you write that, you will get full marks. So multiple oxidation states and you can form complexes. So that is why these transition metals are known for their catalytic activity. So some catalyst, these examples are also important. They might ask you about these examples in the board exam also. So vanadium 5-oxide is used in the contact process. What is contact process? Finely divided iron in Haber's process. Fritz Haber, German scientist. Ammonia. Nickel in catalytic hydrogenation. Yesterday we studied nickel, palladium, platinum, hydrogenation. Same thing. So these are some examples where catalysts are used. Contact process. Does anyone know what is contact process? Does it remind you of sulfuric acid? So, how would you answer this question? This is a previous year question, Gayatri. This is a previous year board CBSE question itself. So, transition metals and their compounds show catalytic activities because of variable oxidation states and ability to form complexes. Then, zinc, cadmium, mercury are non-transition elements. Why? Why are zinc, cadmium and mercury non-transition elements? If I ask you, Sri Ranganath is asking for a 5-minute break in the chat. Bro, you need a break from the break that we took. My buddy living in the future. So how do we define transition elements? Transition elements need to have incomplete d subshell in their atomic or bonded state. Okay, they should either have incomplete D in their atomic state or they should have incomplete D in their bonded state. Yeah. So most of the transition elements have incomplete D, but when you think about something like copper, yeah, copper is a 3D10 4s1. So in its non-bonded state, it is 3D10, but then you can make copper 2 positive also, right? So because copper can make 2 positive ions, 3D9, this is counted as a transition element. But when we talk about zinc, cadmium and mercury, they always have complete D subshell. And therefore they are called non-transition elements or pseudo-noble gas elements also. Yeah. Zirconium and hafnium are almost of the identical atomic radius. Can you account for this observation? Zirconium and hafnium are of almost identical atomic radii. Let me show you a very interesting website just as an excuse to solve this question. There's this beautiful website called ptable.com. Okay. ptable.com. This is an interactive periodic table. So for example, let's say you want to know about the melting point of everything. You click on melting point. Now melting point of all these species in degrees Celsius is mentioned over here. Nice, right? There's a very beautiful website. Anyway, so we were talking about zirconium versus hafnium. Notice where zirconium and hafnium is. If I show you their electronic configuration, where is the expanded configuration? Yeah. Look at zirconium versus hafnium. What has changed over here? Zirconium versus hafnium, the thing that has changed mainly is the fact that hafnium now has these 4f14 electrons. So, from zirconium to hafnium, when we move, there are essentially a lot of 4f electrons that are there. And we know from our pursuits of periodic table in 11th class that f orbital electrons are very poor in screening effect. Yeah, f orbital electrons are extremely poor in screening effect. F orbital electrons of hafnium are very poor at screening. So because of the effective nuclear charge of hafnium, its size is much smaller than expected. Now, as you guys are mentioning in the chat, you should write it. This phenomena is also known as lanthanide contraction. This phenomena is also known as lanthanide contraction. But the thing is that lanthanide contraction, that word is used primarily for lanthanides, because lanthanides keep reducing in size quite drastically. So that word is technically used for lanthanides, but you can use that word over here as well. But if you write these ideas, better explanation. Alright, so lanthanide contraction is a correct idea, but if you explain it, it's even better. In case you are curious to know what their sizes are, let's have a look. Look at the sizes. Zirconium, hafnium, almost the same size. This size is mentioned in picometers, by the way. So zirconium and hafnium almost the same size. Nice. Cool. Let's revise more ideas. Keep solving questions of D and F block. Whole chapter will be revised eventually. Look at the first one. Copper to positive salts are colored while zinc to positive salts are white. Because copper to positive is a D9 species, zinc to positive is a D10 species. So when we make the energy levels of a D9 species, D9 will look something like this. So my dear friends, in the case of a D9 species, electronic transition is possible. Electronic transition. Which electronic transition? From one d orbital to another d orbital. So this can be called a d-d electronic transition is possible. What happens with this electronic transition? When I shine light on it, this can absorb some light. When I shine light on it, this can absorb some light and the reflected light will be colored. Yeah. So if this absorbs, let's say red light, you will see the complementary color. Blue light you will see. Right. So because electronic transition is possible, because color absorption is possible, reflected color will be shown to your eyes. But when we talk about a D10 species, there is no electronic transition possible over here. No D-D transition can take place. So, light that you shine on it, nothing will be absorbed. All of it will be reflected. Full light being reflected means white colored compound. Yeah. So, this is why copper to positive salts are colored while zinc to positive salts are white. Okay. Electrode potential value for the manganese couple is much more than that for chromium couple. Can we think about it? Virendran, we'll do physical chemistry tomorrow, bro. No, sorry, not tomorrow. On Wednesday at 1 p.m. So let us look at the second statement over here. We have manganese 3 positive versus manganese 2 positive. Okay, let's think. Manganese 3 positive. What is the electronic configuration? Manganese 2 positive. What is the electronic configuration? Yeah. What's the electronic configuration of Mn3 positive? This is a D4 species. That is a D5 species. Now, what happens is that D5 is a half-filled subshell configuration. Half-filled subshell is stable. Half-filled subshell is stable. So this is a feasible process. This should happen. This you can call in the language of thermodynamics, this would be a spontaneous process. So the electrode potential would be positive. The electrode potential over here would be positive. But when we compare the ideas behind Cr3 positive to Cr2 positive, people, what is the electronic configuration for Cr3 positive? Cr3 positive is a D3 species. What about Cr2 positive? D4 species, right? Now, why is Cr3 positive stable? It says that Cr3 positive does not want to go to Cr2 positive. Why? Mn3 positive wants to go to Mn2 positive, we explained, because it wants to become half-filled configuration. Cr3 positive does not want to change into Cr2 positive. How do we explain this? Hari Ram, very nice. How do we explain that idea? So the idea can be explained in this fashion. Cr3 positive going to Cr2 positive. This is a D3 species. This is a D4 species. My dear friends, please remember that reduction potential values are measured with H2O as solvent. In electrochemistry, we have reduction potential values, right? Reduction potential values are when we do this reaction in water and we measure the voltage of that reaction. So, reduction potential values are measured with water as the solvent. And with water, Cr3 positive makes a complex like this, CrH2O6 3 positive. And in this complex, what we will have is the crystal field splitting. How can we make the crystal field splitting? I can do this, Eg and T2G. And now we have a D3 species, right? D3, so 1, 2 and 3. Hey, look at this. This entire structure of the T2G level tells us that we have a half-filled T2G subshell. And we know that half-filled subshells are stable. So because of the presence of T2G3 configuration, because of the presence of half-filled T2G when chromium 3 positive inside water, this does not want to change to D4 configuration. So over here, Mn2 positive is half-filled D subshell. That is why this is feasible. This process is not feasible because Cr3 positive already is in a T2G3 half-filled configuration. It does not want to move towards Cr2 positive. That explains this idea. Absolute G's. These are previous year questions of board exams, bro. Alright. Transition metals form alloys. How do you explain this idea? How do or why do transition metals form alloys? What are alloys? Alloys are solid mixtures, right? There are solid solutions, essentially. So the thing is that these transition metals have unpaired electrons that can participate in metallic bonding with other transition metals also. So because of that possibility of metallic bonding, because of their unpaired electrons, because of their d electrons, you form alloys. Okay. Now, how is that idea mentioned in the NCERT? Let us have a look. Alloy formation. Alloy is a blend of metals prepared by mixing the components. Wow. How do you form a solution? By mixing. Alloys may be homogeneous solid solutions in which the atoms of one metal are distributed randomly among the other atoms. It's a solution. Such alloys are formed by atoms with metallic radii that are within about 15% of each other. So, metals with similar radii can get mixed with each other. Because of similar radii and other characteristics of transition elements, alloys are formed readily. So, the 2 points that you can write in that answer is number 1, when metals have similar sizes, similar atomic radius, they can form metallic bonds with each other. Those metallic bonds are formed with the help of their unpaired d electrons. This allows them to form alloys. Okay. So what are the 2 things that you will write? First, you will write similar atomic radius or similar metallic radius. And second thing, the unpaired electrons in the d orbitals can help in metallic bonding across different metals. Cool. So just have a look at the alloys over here. Alloys of transition metals with non-transition metals such as brass, copper and zinc, bronze, copper, tin. These are also of industrial importance. Very nice. Yeah, there is one alloy that is mentioned. I don't know if it's mentioned in this chapter or coordination compounds, but questions from that are generally asked. Yeah, this alloy is also there. Mish metal. JEE and boards, both of these ask you questions about mish metal. So this is in the lanthanides part of this chapter. I'm highlighting this idea for you. So the best single use of the lanthanides is for production of alloy steels for plates and pipes. A well-known alloy is mish metal. Mish metal means mixed metal in German. Mish metal is a German derived word. So mish means mix. So well-known alloy is mish metal, which consists of a lanthanoid metal around 95% and iron in 5% trace. Some traces of sulfur, calcium, carbon, etc. there. A good deal of mixed metal is used in magnesium-based alloys as well. So what is mish metal? Mish metal is a specific type of alloy where lanthanoid is mixed with some other metal. That other metal could be iron, other metal could be magnesium, etc. Perfect. So that is some idea about alloys, what is mish metal, why are alloys formed, etc. Let's move to the next question. This is also previous year question. So, which ion among the following is colorless and why? I'm sure you can figure that out. Which of these ions is colorless and why? One of these ions is a D0 ion. Can you recognize that? We've got scandium, titanium, vanadium, chromium. This is a D1, D2, D3 and D4 species. Yeah, all of them have 4s2 electrons in them. So titanium 4 positive, titanium plus 4 will be D0. There's nothing in the D anymore. 4s0, 3d0. Only thing that's remaining is the 3s2 electrons. Yeah. Not 3s2, but I'm sure you understand what I mean. Noble gas configuration. 3p6. Noble gas configuration. So D0, therefore this should be colorless. No DD transition is possible over here. For these two, DD transitions will be possible. Okay. Why is Mn2 positive much more resistant than Fe2 positive towards oxidation? Quickly. Can you give me the answer? Why can't I oxidize Mn2 positive? Because this is D5, this is half filled. Half filled is stable. Same thing. For 80% of the explanations of D block, half filled subshell is more stable, fully filled subshell is more stable. Highest oxidation state of a metal is shown in its oxides or fluorides only. Justify the statement. Basically, it has to do with the extreme electronegative nature . Yeah. Because fluorine and oxygen are extremely electronegative, they can pull electrons towards themselves from these metals. Okay. So, if we look at the NCERT to see where these things are mentioned, the ability of oxygen to stabilize the highest oxidation state is demonstrated in the oxides. Very nice. Yeah. The ability of oxygen to stabilize the high oxidation states exceeds that of fluorine. Why? Because oxygen can create double bonds also. So because of multiple bond creation capacity of oxygen, oxygen is even better at making higher oxidation states with these metals. So the main idea comes from electronegativity. The main idea comes from electronegativity, but oxygen, because it can form multiple bonds, it can create highest oxidation states very easily. Yeah, there are some ideas given over here about oxides and oxo anions. So you can read about them whenever you get the time. And for JEE exam also, you have to read the NCERT. Because for JEE Main, all questions of inorganic will be directly asked from this textbook. Okay. Very nice. Cool. So that is the idea. Moving forward to these type of questions. These are very interesting, by the way. And what is being given over here is the enthalpy of atomization. On the y-axis over here, we have something known as the enthalpy of atomization. Do you understand what we mean by enthalpy of atomization? Understanding this idea is very important for us. Okay. Understanding this idea of enthalpy of atomization is really important for us. So first of all, let us understand the enthalpy of atomization and then we'll be able to solve those questions quite simply. So, enthalpy of atomization. How do I atomize something? How do I break something into atoms? If I convert something to its gaseous state, I've broken it into atoms essentially, right? Think about a metal. A metal is a solid species. So, you take the solid metal. What you want to do is you want to break it apart into metal gaseous. Because metal gaseous means each atom of metal is far apart from each other. Atomized. Right? So how do I go from a solid metal to a gaseous metal? I simply have to provide it enthalpy of atomization. Yeah. You basically provide it energy to make metal liquid. You provide it energy to make metal gaseous. So this entire process that is there, this can be called the enthalpy of atomization. Now let us try to find some conclusions about enthalpy of atomization. First of all, can I say that more, or I should write it in a different manner. Can I say if I have stronger metallic bonds implies higher enthalpy of atomization? Yes. Stronger metallic bonds imply higher enthalpy of atomization. Very nice. What else can I say? Can I say more boiling point is equal to higher enthalpy of atomization? I am essentially boiling it, no? Subliming it. So you can say higher boiling point implies higher enthalpy of atomization. Perfect. Now, when do we have stronger metallic bonds? We have stronger metallic bonds when we have more unpaired d electrons. When we have more unpaired d electrons, we'll have stronger metallic bonds. But there is an exception. Except for manganese. Why does manganese not give us very strong metallic bonds? Chromium gives us very strong metallic bonds. Chromium is also 3d5, 4s1. Chromium gives very strong metallic bonds, but manganese does not give us strong metallic bonds. Why? Because manganese, the 4s2, 3d5, this species, half-filled subshell and fully filled subshell, this is stable on its own. It's stable enough on its own also. It does not really need bonding. Does not need to bond. Yeah, one fully filled subshell, one half-filled subshell. So it is stable on its own. It doesn't need to bond. Cool. So look at this particular diagram. Which element in the 3D series has lowest enthalpy of atomization? Can you see that diagram? Which metal will be there in the 3D series? Zinc will be there, no? They didn't ask about transition. They are asking about element of 3D series. Zinc comes in the 3D series. Zinc is the answer. Perfect. Why do metals of the second and third series have greater enthalpies of atomization? Can you explain that idea? Why do the metals of second and third series have greater enthalpies of atomization? Why do they make better metallic bonds? Can you theorize that idea? And why are enthalpies of atomization of transition metals quite high? So, let us try to read some ideas about enthalpies of atomization over here from the NCERT. There you are. This is the same diagram mentioned in your look at this. In any row, the melting points of these metals rise to a maximum at D5 except for anomalous values of manganese and fall regularly as the atomic number increases. They have high enthalpies of atomization which are shown in that figure. The maxima at about the middle of each series indicates that one unpaired electron per d orbital is particularly good for strong interatomic interaction. In general, greater the number of valence electrons, stronger is the resultant bonding. Fine. Okay. Since the enthalpy of atomization is an important factor in determining the standard electrode potential of a metal, metals with very high enthalpy of atomization tend to be noble in their reactions. If there is too much energy that you need to break it into atoms, reactions will be very difficult. Okay. Another generalization that may be drawn is that the metals of the second and third series have greater enthalpies of atomization than the corresponding elements of the first series. This is an important factor accounting for the occurrence of much more frequent metal-metal bonding in the heavy transition metals. Okay, fine. So, why is that happening? Why are heavy transition elements getting better bonding? Because of their effective nuclear charge. Okay, those heavier transition elements have inner d orbitals with poor screening effect. So, if you are in 4D series, let's say, the 3D electrons will have poor screening effect. If you are in the 5D series, let's say, your inner 4F14, 4D and 3D, all these electrons have poor screening effect. So, because of the poor screening effect, you have high nuclear charge and that leads to stronger bonding between these metals. Fine. So, that's how that works. Where did it go? Yeah. Fine. So, that is the idea behind this particular question. Enthalpies of atomization of transition metals are quite high because they make very strong metallic bonds. So, see, now similar things will start repeating. Why does zinc have lowest enthalpy of atomization? Because it is not a transition element. It does not have d orbital electrons getting involved in metallic bonding. So the metallic bonds of zinc, cadmium and mercury are very weak. You know mercury is liquid. Why? Because metallic bond is very weak. Yeah, that's why. Transition metals are found to be good catalysts. Now you know the reason. We've done that question already. So repetition, can you see now in previous year questions, repetition has started. There are only a few concepts from which they can ask you these questions. There are only a limited number of concepts. Yeah, okay. So, Kichu, we cannot say van der Waals forces of interaction over here. Van der Waals forces of interaction happen between molecules according to their size. In those molecules, there is no electron sharing. Metallic bond, however, is a bond where electrons are shared between multiple metals. So, a bond is much more different compared to a simple van der Waals force. Okay. Assign the reason for these. Two of these we already know. Manganese exhibits the highest oxidation state of +7 among the 3D series of transition elements. Why? Why does manganese exhibit the highest oxidation state? Can anyone theorize the reason? Why do you think it is so? Think why lower members can't show high oxidation states. Think why higher members can't show higher oxidation states. I'm just trying to find exactly how it is written. Yeah, anyway. Let me explain it to you separately on this page itself. So, my dear friends, look at the transition element series once again. So, we've got scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc, right? Now, this guy shows +7 oxidation state because the electronic configuration is a 4s2 3d5. So this guy shows +7 oxidation state because it has the electrons to show you the oxidation state. These from scandium till chromium do not have enough valence electrons. Yeah. Maximum you can do from here is +6. You get chromium +6. Maximum you can do from here is +5. You get vanadium +5. Maximum you can do over here is +4. Maximum you can do over here is +3. And you do get all of these species. So, for the lower members of the transition series, these do not have enough valence electrons. Okay. Now, what about the other members which are on the other side? Why don't these show you oxidation states like D8, D9, D10, etc.? Because after the 7th electron, removing the 8th electron becomes difficult because of high effective nuclear charge. I'll write that thing down for you over here. After manganese, we observe that the effective nuclear charge of these metals increases and increases significantly. So because of this increase in effective nuclear charge, it is now very difficult to remove more electrons from these elements. Okay, so after manganese, we notice that there is an increase in the effective nuclear charge. And because of that increase in effective nuclear charge, it is not easy to remove more electrons from these particular metals. Therefore, manganese shows you the maximum oxidation state. Hariram, that is a very good deduction that you've made. So if I show you the trend of the radii, just a second. Look at how the radius thing works over here. You have more electrons, so the radius is slightly higher, but you can see a dip from manganese to iron to cobalt. Can you see this dip is there in the atomic radius? So this dip is also accounted for by the increase in effective nuclear charge. Over here it is increasing because there are more electrons. So if you look at their ionic radii, just have a look. Ionic radius for manganese is 137, then it suddenly drops. 126, 125, 125, 128. So this is because of that high effective nuclear charge. Zinc is not transition element anyway. Cool. So good observation. Nice. So we understand the first one, the second one. Cr2 positive is reducing in nature while the same dd orbital configuration is an oxidizing agent. Can you explain this idea, please? We have already done this, no? So I'll leave this to you. I'll give you the hint once again. We've already covered this question, by the way, that Cr3 positive is more stable, and you know the reason why. And you know that Mn plus 2 is more stable, and you know the reason why. So because Cr2 positive goes to Cr3 positive, it acts like a reducing agent. Mn3 positive goes to Mn2 positive, so it acts like an oxidizing agent. Zinc has the lowest enthalpy of atomization, we know. Copper positive is unstable in aqueous solution. Can you explain why? Why is copper positive unstable in aqueous solution? So before I explain this idea of copper positive being unstable in aqueous solution, let's try to understand. Let us try to understand the process that is happening over here. Let's say I want to go from metal to the metal plus 2 state. Let's understand how this process works. This looks like a very simple process, no? That metal is there, it goes to metal 2 positive. But this process in reality is extremely complicated. Understand this process carefully. We have a solid metal to start with, and eventually we end up at an aqueous metal. How will this process work? First of all, we have to take metal solid, convert it to metal gaseous. Why? Because we want to break all the metallic bonds first. We have to atomize it. Once it turns into atoms only, then we can put it into water, right? So, first thing that we need over here is atomization. Then, my dear friends, these atoms will be converted to metal plus 1 type of species. So, what is this process called? When you remove an electron from an element, what is this process called? This is called the first ionization energy. Yeah, so first you have to provide it atomization energy, then you have to give it first ionization energy, then you have to give it the second ionization energy. Right? And finally, there's one more process that happens. This is not complete yet. The final process is when this M2 positive dissolves in water and gets solvated. So finally, M2 positive will become solvated by water. a lot of water molecules will surround it. Remember the amines discussion from yesterday? We understood what is solvation. So this M2 positive will be surrounded by water molecules. And because of this hydration, energy will be released. So over here, hydration energy is released. So this is the entire process hidden inside this reaction. This is simply your electrode potential reaction, but this is the entire process. So think about it. If metal bonding is very strong, if the enthalpy of atomization is high, this process will be difficult. If first ionization is high, this process will be difficult. If second ionization is difficult, this process is difficult. This process will be difficult. You understand what I'm saying? If these energies are higher in value, doing this process will be difficult. If solvation is very good, if the metal is small, has high charge, it will do better solvation. Yeah, high charge density means more solvation. So if solvation is more, this process will be easier. If solvation is less, this process will be difficult. Yeah. So that small reaction at the top depends on these multiple energy factors. Now let us try to understand why copper positive is unstable in an aqueous solution. So that comes from the idea of this trend. Look at this idea. Look at this. The unique behavior of copper. Have a look at the slide given here once again. Look at the electrode potentials. Higher electrode potential means higher tendency of this particular reaction. So the electrode potentials are given from 2 positive to 0. 2 positive to 0. But we want to think of the opposite process. So you think of these with a positive sign. M2 positive to M. This is a reduction process. But you think of the oxidation process. So you think of these with positive sign. More sign means metal easily converts to 2 positive. More value means metal converts easily to 2 positive. Now let's have a look. Yeah. This is your titanium. Titanium easily converts to 2 positive. All of these elements convert to 2 positive quite easily, but copper does not. Copper does not want to get oxidized. What's the reason? Why does copper not want to get oxidized? What's so unique about copper? The problem with copper comes from its second ionization energy. The problem with copper comes in its second ionization energy. So before I show these statements to you, let me once again tell you this. Copper going to copper positive, then going to copper 2 positive. Think about it. This is a 4s1 3d10 species. So this 4s1 is easy to remove. So this value is low. First ionization energy is low. But when we talk about the second ionization energy for copper, this is very high because you're going from 3d10 to 3d9. So over here, from going from copper positive to copper 2 positive, there is very high second ionization energy. So because of this high ionization energy, converting copper to copper 2 positive is very difficult. Okay, converting copper to copper 2 positive is very difficult. Interesting. Now, let me read out these statements for you. The unique behavior of copper having positive reduction potential accounts for its inability to liberate hydrogen from acids. It cannot liberate H2 from acids because itself, it does not want to get reduced. Only oxidizing acids like nitric acid or concentrated sulfuric acid, these can react with copper because they will energize the reaction a little better. The high energy to transform from copper to positive is not balanced by the hydration enthalpy. Yes, we understood going from here to here is difficult because of the second ionization enthalpy. Now that second ionization enthalpy is not balanced by its hydration enthalpy. Copper to positive, it's not hydrated that well. The solvation process is not that great. So it's very difficult to do this particular process. All right. So such questions are asked time and again. In board examinations also they will ask these questions. Right. So you can have a look at these ideas about trends in electrode potential of 3 positive to 2 positive also. You can read this part later after you are done with the session. Yeah. Look at this. Look at this particular statement. This will help you answer that question we had. The stability of copper 2 positive aqueous compared to copper positive aqueous. See, now we are comparing these two. Copper 2 positive with copper. If we force them to form, which one is more stable in water? Copper 2 positive is more stable in water compared to copper positive because of higher solvation energy of copper 2 positive. So once you do the ionization, I took copper, I put energy into it, I did the ionization. Now after ionization is done, if I put copper positive in water, it has only one positive charge. Water will be less attracted to it. This has two positive charges. Water will be more attracted towards it. So because this has higher hydration energy, copper positive is unstable in water. Read this statement. Okay. So what happens to copper plus 1 inside water? Copper plus 1 inside water disproportionates to copper 2 positive and copper metal. Good stuff. So I know you guys find inorganic chemistry a little boring. Everyone finds inorganic chemistry a little boring. But the more you go deep into these ideas, the deeper you go into these concepts, these complex concepts, the more you will enjoy it. It's just that inorganic chemistry needs a lot of patience because things look like you have to accept them at face value. There are more facts and general knowledge than actual explanations. But when you try to dive deeper into these explanations, it actually becomes very interesting. So it just takes some time to get used to inorganic chemistry. Once you do, it's actually quite enjoyable. Now again, repetition. Transition metals form alloys. You know how to answer this. Ce+4 is a strong oxidizing agent. Why? My dear friends, remember one thing. Lanthanides. Okay, remember this in life. Okay. So there will be one day when you are trying to buy a TV from an electronic store. Let's say you're trying to buy an iPhone and you go to the store and then you want to buy the iPhone. That person will ask you, why is cerium +4 a strong oxidizing agent? That will happen to you in life one day. Remember this statement, please. Lanthanides favor +3 oxidation state. All lanthanides want to make +3 oxidation state. So the day you want to buy an iPhone, I don't like iPhone. I like Android. For Android, you don't need this information. iPhone people. Lanthanides favor +3 oxidation state. Please keep in your mind. Go to the Apple store, say this statement, they will give you 20% discount. Lanthanides favor +3 oxidation state. So, if I have a cerium +4, cerium +4 wants to go towards cerium +3. All lanthanides for some reason prefer their +3 oxidation state. So, cerium +4 wants to go to a cerium +3 statement. Fine. How will it do so? It will capture an electron to do so. So, if this species itself is getting reduced, this is a reduction process, it is capturing an electron. So, my dear friends, since itself it is getting reduced, it can oxidize something else. It can capture the electron from something else and oxidize that species. So, cerium +4 will act as a great oxidizing agent. So, Ce+4 is a good oxidizing agent, cerium +4, because lanthanides prefer their +3 oxidation state. Write one similarity and one difference between the chemistry of lanthanides and actinides. What can you say? One difference is that actinides, most of the actinides are radioactive. One similarity is that both of them have lots of f orbitals and they can give you a variety of reactions. Yeah. Last equation, can you complete this? We'll read more about lanthanides and actinides, by the way. Can you complete this particular ionic equation? Cr2O7, 2 negative, 2 OH negative. In basic conditions, how do you modify dichromate? So, let us read a little bit about lanthanides and actinides. Then we'll come to the specific reactions of KMnO4 and K2Cr2O7. Those are also important points. So, have a look. These are your actinides, by the way. And these are all radioactive. Trans uranium elements are all radioactive. Fine. The actinoids resemble the lanthanoids in having more compounds in +3 state than +4 state. Okay. So, the similarity between lanthanides and actinides, this is one similarity that you can give, that they both tend to create +3 oxidation state compounds. Actinoids show in general +3 oxidation state. Lanthanides also in general show +3 oxidation state. That's their similarity. Fine. But the interesting thing is, their chemistry is very difficult. It's very uneven. They create so many weird compounds that actinide chemistry is very complicated. Yeah. And one more thing that is bad about actinides is that because they are radioactive, we can't do much research on them unless you want to risk your life. So, actinoid chemistry is complex and they're radioactive. We don't want to do research on them. Actinides are not very well studied. Yeah. The magnetic properties of actinides are more complex than those of lanthanoids. Okay. The enthalpies of actinoids are not accurately known. There are so many complications. Yeah, let's read this paragraph, which is from that question. A comparison of actinoids with lanthanoids with respect to different characteristics as discussed above reveals that behavior similar to that of lanthanoids is not evident until the second half of the actinoid series. However, early actinoids resemble lanthanoids, showing close similarities with each other. Yeah. So, these ideas that are mentioned in the NCERT, if you have time, you can read them. If you don't have time, leave such a question if it comes in your board examination, right? So, lanthanides and actinides, and these are very important for JEE exam also. So, in case we ever study lanthanoids and actinides for JEE exam, I will give you some ideas about their electronic states, etc. Fine. Now, have a look at this diagram. So all of these lanthanides want to create +3 oxidation states. You can forcibly create samarium 2 positive, europium 2 positive, cerium 4 positive, praseodymium 4 positive. Okay, you can create these species, but they want to turn back into 3 positive. And the graph that is given over here, this is the graph of radius. Can you see how drastically the radius decreases? Can you see how drastically the radius decreases from around 100 something for lanthanum, you reduce to somewhere around 80 for lutetium. So this drastic decrease in radius is because of the poor shielding effect of f orbital electrons called lanthanide contraction. This is exactly where lanthanide contraction word is used. Okay, fine. So can you tell me, will europium 2 positive be an oxidizing agent or a reducing agent? Can you tell me, please? This europium 2 positive, will it act as an oxidizing agent or a reducing agent? What does it want to do? So, europium 2 positive would want to get converted to europium 3 positive. It will lose an electron and this electron can go and reduce someone else. So, europium 2 positive will act as a reducing agent. Fine. All right. So, let me show you some important reactions that are there for chromium and manganese. First of all, let us understand what is dichromate. Potassium dichromate. How is dichromate formed? These reactions are important. Let's read this and then we'll solve those questions. Dichromates are generally prepared from chromates, which are obtained by fusion. Fusion means melting of chromite ore with sodium or potassium carbonate in free access of air. Have a look. So we have our chromite ore and we take sodium carbonate. You can also take potassium carbonate and we have a good supply of air. So when these things are melted together, when you heat them up quite a lot, you get this species. Do you know what this species is called? This is your sodium chromate. Sodium chromate. On the side you get Fe2O3 and some carbon dioxide is released. Now, this chromate, have a look. This chromate, when acidified, if you put chromates into acids, you will get dichromates. So chromates when acidified give you dichromates. Acha, what will happen now if you put dichromate in base? Na2Cr2O7. If I put this in base, then what will happen? The opposite will happen. Okay, the opposite will happen and this will convert itself into NaCrO4. So dichromates will form when chromates are acidified. These like acidic conditions. Dichromates like acidic conditions. Chromates like basic conditions. So when dichromate is put in a base, it will turn into chromate once again. Okay, so you can see that idea mentioned over here also. Chromate plus acid dichromate, dichromate plus base chromate. Alright, very nice. Have a look at the structures, people. This is the chromate ion and that is the dichromate ion. If you want to make simpler structures, you can make the chromate ion something like this. Cr double bond O, double bond O. There is one O negative and there is another O negative over here. And as you can see, what we've drawn over here is a tetrahedral structure. Fine. This is a tetrahedral unit. Now, if two of these tetrahedral units combine with each other, that is when we have dichromate. So this chromium is also tetrahedral, this chromium is also tetrahedral. Two tetrahedral units joined with each other. Alright, so tetrahedral chromate ion, tetrahedral dichromate ion. And remember, we saw the dichromate ion yesterday also. Pyridinium dichromate. Same thing. Alright, so that's how this works. Very nice. Now, this is the equation that was asked in that board examination question. Cr2O7 2 negative plus 14H positive plus iron gives Cr3 positive plus Fe3 positive plus 7H2O. Essentially, they are asking about the chromium's half reaction. Okay, this part is what was asked in that question. So Cr2O7 2 negative, when it does a redox reaction, creates Cr3 positive. And this was a question that you saw in JEE previous year also. The same type of question is asked a lot of times in JEE also. Achha, over here they are taking dichromate and putting it in base. So we have Cr2O7 2 negative. And what happens when I put it in base? Dichromates, when put in base, create chromates. Yes, dichromates, when put in base, create chromate. Very, very nice. So, this is the reaction that they've asked. Cool. You can balance it in this manner. Create some water on the side and balance it appropriately. Chromium oxidation state is Cr plus 6. Both these chromiums are plus 6 oxidation state. Alright. So similarly, let's read a little bit about potassium permanganate also. The process of preparation of permanganate is also important. So potassium permanganate is prepared by fusion of MnO2 with alkali and oxidizing agent. MnO2, alkali, oxygen. Very similar to that process of chromite ore, right? Chromite ore was also similar. This is also similar. Now, when you combine these things together, the manganese over here, which is in the plus 2 oxidation state, this gets oxidized to a plus 6 oxidation state. Right now, what we formed over here is a manganate. Okay, this species that we have is a manganate. Now, this manganate can be converted to permanganate by putting acid. So manganate, when you put it in acid, then you can get your permanganate. Manganate has Mn plus 6, permanganate has Mn plus 7. Alright. So commercial preparation, how it works is, you take MnO2, you put it in KOH, oxidized with air, you get the manganate ion, and manganate ion then can be electrolytically oxidized to permanganate. So this is what you do commercially. In the laboratory, this is fine. Some of the manganese gets converted to the permanganate. A little bit, 1/3 of the manganese gets converted to MnO2. So, if you observe this particular reaction carefully, just observe that reaction. We start with Mn plus 6 oxidation state. We reach Mn plus 7 and Mn plus 4. The same species is getting oxidized and reduced. What will this be called? This will be called disproportionation. Yeah. So, manganate in acidic medium disproportionates to create permanganate, and manganese dioxide. Have a look. Important parts. And make sure you read the NCERT after the class, because questions will be asked from the NCERT. Very nice. So this is some idea about the manganese, permanganate. They are also tetrahedral in nature, by the way. Manganate and permanganate both are tetrahedral in nature. So manganate is green, permanganate is purple. You want to see their colors? You want to see how these crystals look like? Let me show you. Dichromate crystals. If you've seen them in the laboratory, very beautiful looking compounds they are. Potassium dichromate. Beautiful orange looking compound. Okay. So, if you want to look at what a chromate looks like, all chromates are yellow in color, by the way. All chromates are yellow in color. Nice. All chromates are yellow in color. And let me show you what manganate and permanganate look like. It's a very nice dark deep purple color. This is your permanganate. Very deep purple color it has. Cool. And then let's see if we have a manganate over here. Should be there in the chemical reactions. If we can find the color of manganate also, green colored, this one. Dark greenish color. Not a very bright green color though. This type of a dark green color exists for manganate. Anyway, nice. Cool. So both of these, your dichromates, permanganates, as you know, are very strong oxidizing agents. So Cr plus 6 gets converted to Cr plus 3. And for manganese, for permanganate, I hope you remember those ideas from redox reactions, that KMnO4, it reacts differently under different conditions. It gets converted to Mn plus 2 in acidic medium. Fine. It gets converted to Mn plus 4 in neutral medium. I can write Mn plus 4 in a different manner. I can simply write MnO2. So this happens in neutral or faintly alkaline medium. So faintly alkaline means that the pH is around 7 to 8 and it gets converted to MnO4 2 negative in the presence of alkaline medium. So highly basic medium, 7 to plus 2, 5 electron process, plus 7 to plus 4, this is a 3 electron process, plus 7 to plus 1, sorry, plus 7 to, this is plus 6, MnO4, total charge is 2 negative, manganese is plus 6 oxidation state, 1 electron process. Coolio. So see this. In the two tetrahedral structures of dichromate ion, what is the correct statement? 4 CRO bonds are equivalent in length, 6 CRO bonds are equivalent in length, all CRO bonds are equivalent in length. Yes. All 4 bonds will be similar to each other in chromate. In dichromate, one oxygen is different. One oxygen is the bridging oxygen. So that will be different. If you remember the structure that I just showed you from the NCERT, let me show that to you once again. Because of that bridging oxygen, that structure is, this bond length is 179, this bond length is 163. So because there is bridging oxygen, this oxygen's bond length is different in dichromate. In chromate, all oxygen bond lengths are the same. All oxygens are same bond length. So over here, option A is correct. That's 6 CRO bonds are, yes, 6 CRO bonds are equivalent in length. Into tetrahedral structure of dichromate ion. So CR O O O CR O O and O. So basically these three and these three are similar to each other. So technically for dichromate, I should say that the second statement is correct. The first statement is for chromate. So the first statement is correct for chromate, second statement is correct for dichromate. So in this question, since they are asked about dichromate, option B is the correct answer. Fine. Nice. Why is the chemistry of actinides complicated as compared to lanthanoids? Because in actinoids we have higher electrons of the higher shell that are being involved. We have the 6s electrons being involved in bonding, and their bonding is very hard to predict. Upar se, the one more thing is that these actinides are radioactive in nature, so they are complex in their chemistry. Complete the following reaction and justify it as a disproportionation. People, you know, MnO4 negative in acidic conditions will give you MnO4 negative plus MnO2, and if you balance it, you will get this. Yeah. So, people, we just studied it's a disproportionation reaction, so I'm sure you can justify that idea. All boards questions. All previous year boards questions. So now you know the answers to them very well. Nice. So, what is mish metal? Now you know. Lanthanide alloy. KMnO4 plus heat. What will happen over here? KMnO4 plus heat, it will decompose. That reaction is mentioned in the NCERT. Find out how it decomposes. Find it out, okay? Cr2O2, Cr2O7 negative, 14H positive, 6 Fe2 positive. This will give you Cr3 positive, plus it will also give you Fe3 positive, plus some H2O will be created. You can balance this reaction on your own. Redox reaction balancing, 11th class chapter. Transition metal of 3D series that acts as strong reducing agent in +2 oxidation state in aqueous solution. So basically you have to give the reason for this. Transition metal of a 3D series that acts as strong reducing agent in +2 oxidation state in aqueous solution. Because it wants to go to Cr plus 3. Yeah, so you know the reason for that. Cr plus 3, T2G half filled, etc. Great. Transition metal of 3D series that exhibits only one oxidation state. Which is the transition metal of the 3D series that shows only one oxidation state? Apart from zero oxidation state. Can you tell me? We have done this in coordination complexes, by the way. Which one is it? Scandium? Sure. Zinc is not an answer because zinc is not a transition metal. People, are you sure? Or is there something else that you are forgetting? Let's see the table of oxidation states that is mentioned in this particular chapter. Scandium it is. Cool. So, out of all of these, scandium prefers to show you only +3 oxidation state. Zinc shows you only +2 oxidation state, but the problem is zinc is not a transition element. Yeah. Nickel can show +3, +4, but mostly it shows +2. Copper can show both +1 and +2. Yeah. So, scandium is the correct answer. Yeah. Zinc is not a transition metal, so we will not consider that as the answer of this particular question. All right, people. So, what we now need to do is we need to read the NCERT of these chapters. Main ideas have been revised. If you think about it, coordination compounds, we revised almost all the theories. We revised nomenclature, we revised valence bond theory, we revised crystal field theory quite detailed, we revised all the cases of ionization, we revised all the cases of isomerism, we revised Werner's theory also, we revised primary valency, secondary valency. So many things of coordination compounds are revised, even chelation was revised. Very nice. So, when it comes to transition elements, what did we revise? We revised their enthalpies of atomization. We revised, their electrode potential values. Why copper is an exception, we revised that idea. We revised the idea about manganese and chromium and their oxidizing reducing behavior. Yeah. We revised ideas behind alloys. We revised ideas behind metallic bonds. We revised some ideas of lanthanides and actinides. And we also revised the special chemical reactions of dichromates and permanganates and their structures and their colors, their disproportionation, etc. Yeah. So, we've revised a lot of ideas. We've revised lanthanoid contraction also. Very nice. So, lots of ideas that are important have been revised in this class, but this was a revision session. We were not here to do full chemistry just 2 days before the board examination. That is impossible to do, and that does not make sense to do either. So, further revision of the concepts that are there in these chapters, which are not as important, but question can be asked from them, you have to read the NCERT and revise. All questions that are there in NCERT, same type of questions will be asked in the board examinations. So people, this would be your homework. So technically speaking, this class is over. If you want to leave, you can leave. Thank you so much for joining in. And tomorrow, I have a class on my Hindi channel, Vedantu JEE. So there I have to do this marathon session for boards revision. I will do mostly question solving in that particular session. And day after tomorrow, on Wednesday, on this channel at 1 p.m, we have the session for physical chemistry. Okay, so that's our plan. So if you want to ask me any other stuff, any miscellaneous doubts, you can ask me right now, and then I will take your leave. Nikhil, if you're asking about JEE previous year questions, then we will do that after the board examinations are over. We'll see, we can do that for sure. In case there is demand for problem solving sessions for the April attempt, I will definitely do that for you guys. Julio. Kichu, on this channel, I will always take classes in English. Mohan, I will try to do, but on Vedantu JEE tomorrow, that marathon session that we have, Hindi language, I will do mostly question solving because we don't have enough time to go into the details of each and every chapter. So I will mostly be doing question solving in tomorrow's session. Mohan Rajyo, man. Vignesh, almost, yeah. We had a 10-minute break in the middle. Rohan, what's up, man? Sashwin is saying, what about synergic bonding in metal carbonyls? You can revise it from the NCRT. It's not very difficult. What happens is that one of the anti-bonding orbitals gets involved in resonance with the d orbital electrons. Just have a look at it from the NCRT. You'll understand it very easily. Ranjan, disproportionation reaction is basically when the same species gets oxidized and reduced at the same time. Revati, I stay in Bengaluru. Sumit, the questions that I solved in the class, these are the more important concepts. Apart from these, you can solve 2024, 2023 boards previous year questions for D and F block for your board exam. Sharmi, it's okay, doesn't matter. Gagana, tell me, what's the problem? Raghu, just search for it on Google, man. You'll find lots of practice papers. Bhuvan, nothing, bro. You can think about the more electron donating group, the more activating group is what decides the final place of attack. Kraken God, if you want mesomeric effect in detail, watch this series called 𝒂𝐴𝐺𝐸. If you guys want to become good at general organic chemistry, just watch it. Zoya, I will share the session PDF once the live session is over. Kevin Santosh, depends on the charge outside it. Usually it is a PtCl2En2. If you don't have any charge outside, then platinum is +2 oxidation state. If you have a +2 charge outside, then platinum is +4 oxidation state. We did that question today. Please check it out. Melvin, depends on how much time I have. If I have time and if we have demand for NEET classes, then I can do that as well. Sharmi Singh, can you say any tips for chemistry board exams? Write it neat and clean. Make sure you solve the questions in the same order as they are given in the question paper. If you do it here and there, then the person who's checking your exam will be in a difficult position. If you do it according to the sequence of the question paper, it's easy for the person checking your examination. Yeah. So try to do that. And if you guys don't know this, let me tell you. On CBSE's official website, CBSE Board's official website, you can find answer sheets of previous year toppers. So previous year boards toppers, they take their answer sheets, scan them and upload them online. You can download that and see how they present their paper. And look at that presentation and try to learn how to present yourself in the examination. Sashi is saying, if we don't know the answer, how to answer? Leave that question. If you don't know the answer, just leave that question. Okay. Umar, bro, right now I can't do so because I don't have enough time in this session. But if you want to learn about the atomic structure from me, then you can look for my classes in this channel called Catalysis by Vedantu. They're all in English. And there is a series over there called What's in the Atom. You might be able to understand some ideas from there. AKO, man, we're neighbors then. Raghav, as I told you, you can see the previous year toppers answer sheets and see how they've represented the diagrams. Mohan is saying, per chapter, how many previous year questions will solve? I don't have a plan, Mohan. for that. When you feel like you're done, you're done. That's how it works. Sanjay is saying, can you give strategy for JEE Advanced 2025? Solve as many difficult questions as you can. Solve all the JEE Advanced previous year questions, Sanjay. Okay. Cool. Suntari, we had a full session of organic chemistry yesterday. You can go and check that out. That'll help. Vishwa, cool, bro. Nice to see you here. Kevin, just search for them on Google. There are lots of websites that give you previous year questions of all examinations for free. So you will find it. Sharmi, the motivation that I can give you is exams are so close. Once you're done with the exams, you'll enjoy so much because you'll be free, at least for some time. Take these exams properly so that you can be happy when you're free. That's my logic for motivation. Umar, yeah, why not, man? Okay. Gagan, it's usually a blue colored pen that you have to use. Ashwin, it can. Theoretically, yes. Nihara, if you have not done anything and today you start and board is on 27th, it is difficult. This will help. Akilan, synergic bonding, you can refer to the NCERT once to study it. Okay, so let me give you an idea of synergic bonding, sir. Multiple people are asking about it. So let me give you an idea about synergic bonding. This is metal. This is carbonyl. These two electrons, yeah, which are given by carbonyl. These two electrons that are given by carbonyl. Where are these going? So these two electrons are going inside the D of the metal. Carbonyl is the ligand. So the main bond that is formed is by the two electrons of carbonyl going inside they go to a D orbital of metal. Or I shouldn't say D orbital of metal, I should say they go to a hybrid orbital of metal. Yeah, so this hybrid orbital could be your D2sp3 or sp3, D2, etc. Yeah, so you know where ligands metals are going in the metal, you know where ligands electrons are going inside the metal, you know that. But at the same time, can you think about the molecular orbital diagram for carbonyl? Carbonyl is a 14 electron species, so the molecular orbital diagram looks pretty similar to that of nitrogen. Sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, 2, 1, 2 and 1, right? So if I fill the 14 electrons over here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, right? So basically, these electrons are making your coordinate bond. Fine. Now if I name these orbitals, this is your sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. This is your pi 2p x and y. This is your sigma 2p z. These are your pi star 2p x and y. And this is your sigma star 2p z. Now the thing is that this metal also has some electrons, right? Metal has its d orbital electrons. So metal's d electrons can go and sit inside this orbital. So ligand puts its electrons in metal's orbitals, metal puts its electrons in carbonyl's orbitals. Okay? Metal puts its electrons in carbonyl's orbital. Which orbital? This one. This pi star orbital. This anti-bonding orbital. So my dear friends, when we go from bottom to top, this is known as the highest occupied molecular orbital. This one is called the highest occupied molecular orbital, and this one is known as the lowest unoccupied molecular orbital. So HOMO electrons go towards metal and metal's electrons come towards LUMO. This two-way bonding is known as synergic bonding. Okay, so this two-way bonding is known as synergic bonding, and this is illustrated by diagrams very well in the NCERT. There we are. Have a look. Yeah, carbonyls, sigma, electrons are going towards metals orbitals, and metals electrons are going towards the pi star orbital of carbonyl. Yeah. So you can read about this idea. The metal carbonyl bond in metal carbonyls possesses both sigma and pi character. The metal carbon bonds sigma is formed by the lone pair into metal, and the pi bond is formed by metal into ligand. So the vacant pi star orbital is filled by the metal's electrons, as we have mentioned over here. So that is the idea behind synergic bonding. Very nice. Ashwant, I wouldn't say full marks, but at least like 90% marks you can get from that video. Umar, you can, but it is difficult to do. All right. Cool, people. So I think I will take your leave. Thank you so much for joining in. And once again, I'm going to see you guys on Wednesday. And on Wednesday, we will do physical chemistry. Yeah. And for physical chemistry, we will do only question solving. Mostly we'll do question solving because numerical type things are there. And while solving questions, I will revise some ideas for you. So electrochemistry, solutions, colligative properties, and chemical kinetics. So if you can do a little bit of practice before that question, it'll be much, much beneficial for us. All right, people. Thank you so much. Take care. Bye-bye. Leave your comments later and I will answer them when I get the time.